This video is a compilation of our main videos in the channel dedicated to the mathematics of general relativity. Many people commented on our videos and emailed us asking for an organized and ordered sequence of videos so that people can learn the mathematics required to learn general relativity. And this including our PDFs as well. So this right here is going to be a very good introduction level content. This compilation is going to be very helpful for anyone who already knows multivariable calculus and linear algebra to learn the basic math underlying general relativity. We structured it into 20 chapters, all of which have our PDFs attached in the description. Warning though, we didn't try to be excessively rigorous here. We didn't get into too much detail. Rather, this is an overview with intuition and the minimal mathematical knowledge to let you guys start studying the most traditional general relativity books. Their links are in the description. We covered tensors, differential forms, Riemannian and pseudo-Riemannian manifolds, the different ways to measure curvature in differential geometry, some classic solutions of Einstein's field equations, as well as how to get to them, and other concepts that will help you to go from a classical view of physics to one that better fits relativity. So, let's start it. Chapter 1. Manifolds. In the first chapter, we explain what manifolds are, and how their construction isn't something random, but actually these are concepts that come naturally when we're trying to describe the spaces involved in differential geometry and general relativity. So, very abstract spaces. To put it simply, a manifold is a topological space that locally resembles a Euclidean flat space, which means that if you zoom in enough, it behaves like a space with zero curvature. How can we describe the space around us? If we take a room, it can be broken down into a combination of points, lines, which can be extended indefinitely in both directions, planes, angles, and the distance between them. This is the first immediate assumption, if we just look at the surface of things, and it is based on classical geometry.
But what if we overlay Cartesian coordinates on pretty much any surface we want in that room? Well, then we'll have a 2D representation, pretty much like a plane, but with coordinates that can be labeled x and y, which allows us to pinpoint locations on the plane. This is what we refer to as R2. However, to capture all sides of an object, we move to a three-dimensional space R3, where instead of having just two directions x and y, we have three, z being the third, allowing us to describe any point with three coordinates. But we don't have to stop here. We can go on and increase dimensions.
The concept doesn't have to be confined to just 3 dimensions. We can conceptualize Euclidean spaces in higher dimensions as well. A Euclidean space can be n-dimensional, holding all possible tuples of n real numbers, x1, x2, all the way to xn, with each number representing a coordinate in one dimension of that space. The distance between 2 points x1, x2, and so on to xn, and y1, y2, and so on to yn in Rn is given by the following formula. This is a generalization of the Pythagorean theorem. In itself, we just described a Euclidean space. But did you know that if we zoom out, we actually described a manifold, but locally?
Think of it like this. If we have a line, we can turn the ends out to form a circle. But if we zoom out on a tiny piece of the circle, it looks very much like a line, locally speaking. This is a pretty important idea to grasp, because pretty much any closed loop in one dimension is a manifold. Let me explain. The idea is that at a very small scale, every part of the loop looks just like a tiny segment of a straight line, despite the overall curved shape. Thus, you can find a continuous one-to-one mapping from that straight line to a closed loop. So in other words, they are homeomorphic. Open-ended or even infinitely extending curves like parabolas, hyperbolas, and cubic curves still have a local structure similar to a line, making them 1D manifolds as well.
But not all closed shapes fit into this definition. If you guys are enjoying this video, please do not forget to like it and to subscribe to the channel. This really helps us. For example, the number 8 has an intersection in the middle. And this crossing point, no matter how you zoom in on it, will not resemble a single line locally. The same thing can be said if we increase the dimension to 2. The simplest thing you can start with is a sphere. Locally, you can imagine that it looks like a flat plane. And again, the two are homeomorphic. Thus, any two-dimensional surface that doesn't self-intersect is also a two-dimensional manifold. Of course, we see that every day with the Earth. Looks flat to us locally, but it's a sphere globally.
We can go on to higher dimensions, but they're pretty difficult to imagine. So what can we do? Say we have a manifold, and we call it M. We imagine it to be embedded in an n plus k dimension. The n refers to the dimension of the manifold itself, while the k represents additional dimensions that are not part of the manifold, but are part of the surrounding space in which the manifold is embedded. On this manifold, we're supposed to have coordinates, right? But how would you know where to place them in higher dimensions? Well, we have patches, called local coordinate neighborhoods. One u alpha and u beta, and they are collections of points, or open sets. This means if you pick any point within this neighborhood, you can find a small circle in 2D, or sphere in higher dimensions around this point, that entirely fits within this neighborhood. It means that locally, the environment around any given point on the manifold can be described in terms of Euclidean geometry, even if the manifold itself might exist in a higher or more complex space.
Now remember, since M is a manifold, we can associate or map each point of the manifold with exactly one element of a Euclidean space, Rn. This is done via a function phi. Suppose P is a point in U alpha. Applying the chart phi alpha to P might convert the geographical position of P into a pair of numbers, representing its coordinates in a 2D plane, say xy. This mapped point is called the coordinate or local coordinates of P in our chart or coordinate system.
Now these small circles around the points can create gaps and not cover the entire manifold. Because of that, overlapping areas exist. They provide a safety margin to ensure a complete cover of the manifold without any gaps. Since each chart maps a part of the manifold to Euclidean space, overlaps ensure that there is no point that is left unmapped, because boundaries of charts might not align perfectly. If we have a bunch of charts that together cover every point on a manifold, it's called an atlas.
When two charts, like phi alpha and phi beta, overlap, the functions that convert coordinates from one chart system to another are called transition maps. This function translates coordinates from the phi alpha system to the phi beta system. This one translates coordinates from the phi beta system back to the phi alpha system. They can also be represented as T alpha beta and T beta alpha. These maps are defined on the overlap of the chart's domain. Specifically, phi alpha beta works within phi alpha of U alpha intersection with U beta, and phi beta alpha within phi beta of U alpha intersection with U beta. These areas are where both charts provide valid coordinates for points on the manifold. The smoothness or differentiability of manifolds is characterized by how many times you can continuously differentiate these transition maps. The derivative represents the rate at which one quantity changes with respect to another. For functions from real numbers to real numbers, like f of x equals x squared, the derivative at a point tells us the slope of the tangent line to the graph of the function at that point. The derivative itself varies smoothly without any abrupt changes or any jumps as you move along the curve of the function.
Thus, this smoothness is what allows us to do calculus on manifolds. Being able to continuously take derivatives up to a certain order k means you can compute the first, second, and kth derivatives. And each of these derivatives is a smooth function itself. Continuous is the simplest level of differentiability, where functions are just continuous, with no sudden jumps.
C1 are functions that are smooth enough to take one derivative, like going from a straight line but potentially cornering path to a smoothly curving path. In CK, k times differentiable, you can take k derivatives, one after the other, and all of these derivatives are smooth. C-infinity are smooth manifolds, and it's the highest level, where you can take any number of derivatives, and all of them are smooth.
Keep in mind that when we have smooth mappings from a manifold to a lower dimensional Euclidean space, it simplifies our analysis a lot. Trying to analyze a manifold that is embedded in a higher dimensional space is extremely difficult. But when we work within the more familiar and more manageable context of a lower dimensional Euclidean space, the analysis becomes relatively easier.
Now, this is how you get to a manifold, but how to perform operations on it deserves a video on itself. Also, do not forget that in every video, we're adding a PDF link in the description below, so that you guys can follow in detail all the calculations we do in this video. Remember, that's really the only way to learn math, by practicing by yourself, by trying to reproduce everything independently. So I highly recommend you guys downloading the PDF link in the description below. That was a broad overview of the mathematics behind manifolds. We kept things intuitive, with just enough structure to get you guys started. Chapter 2. How to do calculus on manifolds. We know that the tools of calculus, like limits, derivatives, and integrals, only work in Euclidean flat spaces. And the problem we run into in differential geometry and general relativity is that we're trying to apply these powerful tools to spaces that are way more abstract, like curved spaces, or more specifically, manifolds. Even though manifolds are locally flat, they are not globally flat, so we don't have the guarantee that we can use the tools from calculus. We'll find a mathematical trick that will allow us to get around this problem. Step by step, we'll build intuition, from simple paths to tangent vectors. And we'll see how we can represent velocity and changes in spaces that are not necessarily flat. Take a space which looks like a bunch of rectangles stitched together. That's a Euclidean space, much like the intuitive kind we experience around us. But if we zoom out, we see that these stitched rectangles are actually a sphere, which exists in a three-dimensional space. The sphere is a manifold. Because we can go back and forth between these states with ease, from a flat plane to a curved ball, they are locally homeomorphic. This is a crucial property, because there are certain spaces where, if you zoom in on them, they do not resemble a Euclidean space, and therefore cannot be manifolds. Anyway, what can we do with a manifold? Say we want to calculate distances on the curve of the manifold. What can be done?
Say we have a manifold M, for manifold. In order to measure the distance of the curve, we need to use a tangent space for a point P on the manifold. Say we trace a specific path on M, called gamma, through the point P. You can think of gamma as the trajectory of a moving point. This path is parameterized by t, meaning t is a variable, like time, that allows us to describe the position of the point on the path at any given moment.
At a specific value of t, like t0, the point on the curve is at location P on the manifold. As this curve gamma moves through P, its velocity at P is not just about speed, but also direction. It's where and how fast the curve is moving at that exact point. This creates a tangent vector located precisely at point P, which for now we'll call it V. It's like if you were walking along a path and at a specific moment you noted your speed and direction. That's what the tangent vector captures.
This figure is a bit misleading, because the tangent space doesn't literally look like a tangent plane, tangent to the manifold. It's something abstract. It can look like this when it is embedded in a higher dimension space, like we have here, which helps us visualize it. Essentially, this entire explanation just helps us get a good intuition of things. But manifolds can also exist in higher dimensions like n. So how can you possibly imagine a manifold existing or embedded in 4 dimensions? Or 5? Or 10? Well, we can't. But we can zoom in on them. Not in the literal sense, through applying functions on a particular point on that manifold, and work on it in the intuitive realm of a Euclidean space. See, we have a manifold M, but this time in n dimensions. If we want to pick a specific point on it, how would we know its location? Well, we actually need to create a sort of neighborhood of points, called U, which is formally called an open set. This implies that for every point in U, there exists a neighborhood around a point, which is entirely contained within U. We can pick a point within U and label it P, for point. Pretty straightforward. P has some room to move within U without immediately stepping outside U. So P is basically floating somewhere in U. Now let's convert or map U onto a Euclidean surface.
Mathematically, This is represented as phi from U to Rn, where phi is a coordinate map that maps U homeomorphically to an open subset of Euclidean space Rn, meaning that it preserves the structure of the manifold locally. This setup makes it possible to do calculus and other mathematical operations in a more intuitive way because we are using the Euclidean space. On the original manifold, we have a curve that runs along it, gamma, where t, like time, or any other continuous variable, is the parameter. It's represented like this, and it's read like gamma is a map from t to m. Gamma is a function or a map that takes in a parameter t and returns a position, a point on the manifold M.
As we established previously, for each value of t, gamma t gives a point on the manifold. If t is thought of as time, then gamma t would describe the position of a particle or moving object on the manifold at time t. The arrow shows that the function is mapping, or sending, values of t to corresponding points on the manifold. In this curve, t ranges from the initial value a and the final value b. It's like starting at hour 0 and ending at hour 10, just as an example. All of this is expressed by t in ab to m. Now, we want to imagine that we are walking along this curve, but not on m directly, but on the local coordinates. In other words, this mapping to Euclidean space we talked about earlier.
We take gamma of t, the curve on the manifold M, and phi, the coordinate map that takes points from the manifold and maps them to local coordinates in Rn. This gives us a compositive function, made of combining two functions together. When you compose phi and gamma, you're essentially translating the curve from the abstract manifold M to the local coordinates of Euclidean space Rn. So the function phi composed with gamma takes the parameter t and gives you a vector of coordinates in Rn, or the local Euclidean space.
So finally, how can we compute the velocity of a point moving along the curve on a manifold, but express it in local coordinates? After applying the map phi, the curve gamma of t on the manifold is now represented as x of t in local coordinates. So x of t is a vector of coordinates that tells us where the point is in Rn, the local Euclidean space.
The curve gamma of t on the manifold M is now represented in terms of local coordinates x of t with components x1 of t, x2 of t, and so on until xn of t in Rn. This is saying that x of t is a vector of n components, where each component xi of t represents one of the coordinates in the local Euclidean space Rn at time t. So, to recap, the velocity of the point on the manifold at time t is the rate of change of the position vector x of t with respect to the time t.
In case you didn't know, we define velocity as the derivative of position with respect to time. The reason we use a derivative is that the velocity measures how quickly the position changes over time. The derivative gives us the exact rate of change. So to find the velocity vector, just like the one we looked at in the beginning, specifically at p, for example, we take the derivative of xp of t. It's because of this composite function that we can do calculus in curved spaces, since this is a function from the Euclidean space R to the Euclidean space Rn. I know this was a lot, so in case you didn't catch everything, know that we've attached a PDF down in the description. Remember, that's the only way to learn math, by doing it and practicing by yourself over and over again until you eventually get it.
In conclusion, even though some manifolds are not flat, we saw how we can use the tools of calculus when we're working locally. This idea of zooming in and using tangent spaces is exactly what allows us to do calculus in curved manifolds. Chapter 3. What differential geometry is all about. We're used to doing calculus in flat familiar spaces, like drawing a line and seeing how it evolves over time, calculating its rate of change, and so on. But what happens when that curve lives in a curved space, like a curved surface? In this chapter, we're interested in how to do calculus in curved spaces, so that we can see technically how we can do it in detail. Imagine we have a point here, and it moves around in the space where it lives.
We can trace its path by simply painting where it's been. This will create a curve. Since in this case the curve lies on the plane of your screen, we can assign a coordinate system with the origin wherever we want, and then parameterize the curve.
This parameter t plays a very similar role to time, but not necessarily. It is useful though to think about it as the input and the vector given by the coordinates of the point as the output.
So for every input of time, there is an output of position. This will allow us to not only draw the curve formed by the path, but also to do calculus on it. We could calculate limits, derivatives, the integrals, and so on.
But all of this is possible only because this curve, which we'll call gamma, takes inputs in R and returns outputs in R2. In other words, gamma is a mapping from the Euclidean flat space R, which is the real line, to the Euclidean flat space or surface R2.
But what if we tell you that actually, all of it is happening on a curved surface, and that we just thought it was flat because we were too close to perceive the curvature of the space around us? Well, if this is true, then our situation really sucks because of all the calculus we just did. Namely, limits, derivatives, integrals, etc. are just wrong. We cannot do calculus anymore because now we found out that actually gamma is a mapping from the Euclidean or flat space R to the non-Euclidean, so not flat curved space M. We usually call this space M because it is a manifold.
A manifold is a space in 1, 2, 3, or even n dimensions that can have or not have curvature, but most importantly, that looks like a Euclidean flat space locally. A very good example is the Earth, and the fact that we cannot perceive the curvature of the Earth just by standing on it. Locally, it looks flat, so we say that the Earth is locally a Euclidean space, or simply a manifold. Don't ask a flat earther though. They don't know the difference between a Euclidean space and a manifold.
Anyway, now we have a very peculiar situation. The curve gamma that describes the path we are interested in lives in the manifold M. And what is really tricky is to visually understand the fact that M does not live inside of any other space. Of course, it is really hard to represent it on a screen, but all you need here is to convince yourself of the fact that M is a space of its own, such that it does not need another larger space where to live in order to exist. In mathematical terms, we say that M is not embedded in higher dimensional space. If you're enjoying this video, don't forget to like it and to subscribe to the channel.
So, how do we fix the problem? I mean, we still want to be able to do calculus on the manifold. And that's where differential geometry comes in. This subject gives us all the necessary tools to achieve our goal. So now that we understand the situation from the intuitive point of view, and that we clearly stated the problem we're trying to solve, let's level up the discussion.
Picture an abstract manifold M with dimension n not embedded in a higher dimensional space like Rn. Then we pick a point P in it, and a small neighborhood U around the point P. We can define a parametrized curve passing through P, called gamma of t, that goes from an interval AB in R to M. Its image in M is the interval gamma of A, gamma of B. Let's also impose that the entire curve is inside the neighborhood U.
Next, we define a mapping phi from the neighborhood U in the manifold to Rn, with image phi of U in Rn. N is the dimension of the manifold M, as well as the dimension of the Euclidean space Rn. Since we can create a composite mapping, phi composed with gamma, from the interval AB in the real line to Rn, we can also do calculus here, because this is a mapping from a one-dimensional Euclidean space to an n-dimensional Euclidean space. But what do we mean by do calculus?
Well, we'll see it shortly, but first, some important remarks. The manifold M cannot be described using the traditional x, y, and z, so the Euclidean coordinates, because it's not necessarily embedded in Rn. So, we need to define instead intrinsic coordinates uv, which will serve as a sort of grid used to measure distances in M. Actually, in order to measure distances, a metric must be defined. And by the way, when applying this to general relativity, the metric is usually defined as g, and it describes gravity on the manifold. Another important remark is that the mapping phi from the neighborhood u in M to Rn is called the local chart by mathematicians and coordinate system by physicists.
Let's see a concrete example now. We have an abstract 2D manifold M, which is paraboloid shaped, but it's not embedded in R3. Pick a point P in M, and let U be a small neighborhood of P. This neighborhood U allows us to work locally on M. We cannot use the traditional x, y, z coordinates of Euclidean space. Instead, we'll describe it using intrinsic coordinates uv. Define gamma from 0, 10 in the real line to the manifold M as a parameterized curve on M. The domain 0, 10 in R serves as the interval of the parameter t, and the image of gamma is the curve on M. Let the curvature gamma of t, which is u of t and v of t, represent the path in terms of intrinsic coordinates uv on M, where u of t is going to be defined as t and v of t, t squared.
Here, u of t, v of t represent the coordinates of the curve gamma in the intrinsic coordinate system uv on M. But we still didn't talk about how these intrinsic coordinates uv will look like globally on M. The intrinsic coordinates act like a grid on M. In our case, we picked our grid to represent directions and distances on M, similar to polar or geodesic coordinates that vary smoothly as we move across the surface. We're not going to go into detail here, but if you want to know more about how these intrinsic coordinates uv are defined, check out the last pages of the PDF in the description below.
Let's talk about the local chart phi now. Define a mapping phi from U to R2, which flattens the neighborhood U in M into R2. Phi of UV is going to be defined as just UV. This is a very simple mapping that takes the intrinsic coordinates UV and directly maps them in R2. Now we compose phi with gamma. Phi composed with gamma goes from 0, 10 in the real line to R2. And in this case, phi composed with gamma of t is going to be t, t squared, which is a parabola in R2.
This is a composite mapping from a one-dimensional Euclidean space R to a 2D Euclidean space R2. And therefore, we can do calculus on it. The first one is differentiation. The derivative of phi composed with gamma is the derivative of its coordinates, which results in the vector 1, 2, t. This is the tangent vector from t equals 0 to t equals 10. If t represents time, then this vector is the linear or tangent velocity at each point of gamma. Now, an important question is, where does the vector 1, 2, t live? One could say that this vector lives in the manifold M, but it doesn't make sense even from a visual point of view, because the manifold is curved and a vector is straight. Of course, assuming that we're using the simplistic view of a vector as an arrow. So the tangent vector would stick out of M. But this representation is nonsense as well, because we said that the manifold is not embedded into another higher dimensional space. So it doesn't make sense to draw anything outside of the manifold M. There is no outside world with respect to the manifold. So our representation here was actually wrong.
At this point, one could say that the tangent vector 1, 2, t lives in the space R2, where phi lands. But this is also not completely true. The tangent vector actually lives in the tangent space of the point phi composed with gamma of t, which is actually another distinct copy of R2.
We notice that for t equals 0, 1, 0 is the tangent vector, or velocity vector if you will, at the initial point gamma of 0 in the manifold M. And for t equals 10, 120 is the tangent vector at the initial point gamma of 10 in the manifold M. We can also see that this tangent vector increases linearly from the initial point to the final one along the curve gamma.
Second, magnitude of the tangent vector and integration. The magnitude or Euclidean length of the tangent vector is this. So the square root of 1 plus 4t squared. In order to find the arc length of the curve in R2 from t equals 0 to t equals 10, we integrate the magnitude of the tangent vector over this interval. This integral represents the length of the path t squared in R2 and can be evaluated as follows. We'll show the calculations really quickly here. But if you want to study them in detail, which we highly recommend you doing, check out the PDF link in the description. Otherwise, you can just skip to the final result. After updating these results, we finally get this approximation. 101.05. And this is the approximate length of the path t squared in R2.
Third, curvature. To find the curvature kappa of the path t squared in R squared, we use this formula, where x is t and y is t squared. Let's calculate it. This curvature describes how sharply the curve t squared bends at each point in R squared. When t tends to 0, kappa of 0 is 2, which implies that the curvature is highest at the start. When t tends to infinity, kappa tends to 0, which implies that the curve flattens out as it moves farther from the origin.
That's it for today, but check out the PDF link in the description. There you'll find a more detailed explanation of these concepts. So the moment we realize that the curve lives in a curved space, everything changes. Calculus doesn't break necessarily, but we need a new perspective. And that's exactly what manifolds give us. Chapter 4. Tangent spaces in differential geometry. In differential geometry, curves and surfaces are spaces where we can do calculus on. But how? And that's exactly where tangent spaces come in. At every point on a manifold, there is a tangent space, a flat linear approximation that tells us how we can move, differentiate, and define directions locally. We've seen this before with lines that are tangent to curves, which is a very simple case of it. Now we extend this to full tangent spaces, or even in higher dimensions. And these spaces are not necessarily embedded in other higher dimensional spaces. So there is no ambient space. In this chapter, we'll discuss how we can construct tangent spaces and how they live on the manifold without needing an external space to sit in. We use charts to connect curved geometry to Euclidean calculus. We'll even build the basis for these spaces. Think of a curve. We'll locate this curve in a dimension which we can easily imagine, in 2 dimensions. Now, draw a line which lightly touches the curve at just one specific point. This is a tangent line. Now, say that instead of a line, we draw a 2-dimensional space, much like a loosely hanging sheet. This is a manifold, by the way, and it is located in a 3-dimensional space. Say we pick a point P and want to draw something equivalent to a tangent line but in 2 dimensions. We would therefore draw a tangent space. In this case, it looks like a flat plane just touching the point in exactly one place. It's labeled TPM and literally means the tangent space of the manifold M at point P. Mathematically, we would describe the tangent space just like how we describe locations in everyday space using coordinates like x, y, z in 3D, and we describe directions in the tangent space using coordinate systems tied to the manifold. On a 2D manifold, we might use coordinates like x1 and x2, and these are local variables that change smoothly as we move around the manifold. These coordinates help us describe the position of a point on the manifold, and they also help us to describe directions at the point P in the tangent space.
Well, what's the point? So what? We drew a plane lightly touching a point. Now what? Well, actually, these tangent spaces are abstract constructions that represent all possible directions in which one can move from a point on a manifold. This concept is known as a vector. Vectors are arrows which have direction and magnitude. Much like going and then all of a sudden stopping and noting how fast you were walking and in what direction. On a curved line, there are only two possible directions for vectors: forward and backward along the curve. On a two-dimensional tangent plane, there are infinitely many possible directions, forming a circle of choices, or directions, around the point P. They are important because they describe how steeply a curve climbs or falls at a point. When we have a higher dimensional manifold embedded in a higher dimensional Euclidean space, these vector spaces become more abstract and impossible to visualize. These spaces still touch the manifold at one specific point. But here's the catch. Manifolds don't actually need to be embedded in a higher dimensional space. They kind of exist on their own. We study them abstractly, independent of any embedding. Let's see if you got that. A manifold does not have to have a space surrounding it. It is the space, and there is nothing beyond it. That's why vectors can't poke out of it, because there's nothing to poke out into.
Instead, to find vectors and perform calculus, you have to pick a point and localize it, or conceptually separate it from the manifold itself. This is similar to zooming in on a globe of the Earth until it looks flat, except the Earth is the only thing that exists. There's no space surrounding it. That's what we are doing conceptually when we use charts to map part of a curved manifold onto Euclidean space, where we can perform calculus. So again, we can only properly measure things when we embed a portion of the manifold to locally resemble a Euclidean space.
So the question becomes, how are we supposed to do that? And how would you map an entire tangent space? First, let's start with finding out just one single vector. We have a manifold M and pick a point P. Since we are talking about a manifold in higher dimensions, it's pretty hard to pinpoint the exact location of the P. So instead, we create a neighborhood of points where P floats freely, but does not exit the boundaries of the region, and label it U. It is formally called an open subset of M. In order to perform any kind of calculus at all on P and on U, we have to map it to a Euclidean space Rn, where calculus is well defined. This is done using a chart phi. This chart assigns local coordinates that describe the point on M near P. These coordinates let us flatten the manifold onto Euclidean space, where we can do calculus.
So, say we have a curve gamma passing through the manifold through the point P. Here, we also have to map the parameter of time, or t. Remember, we need to find the velocity of the vector, which includes the component of time, not only where it finds itself geographically, t, which finds itself in another Euclidean space, R. The line itself is just one-dimensional, representing time. T takes values in the interval AB in the real line, and therefore we map t to the manifold M, using gamma. The parameter t tells us where we are on the curve at a specific time. For example, gamma of t0 equals p, which means that at time t0, the curve passes through the point P. To calculate the velocity of the curve at P, we need to work in a Euclidean space Rn, where derivatives are well defined. To do this, we combine the chart phi and the curve gamma of t. The composition phi composed with gamma maps the curve on the manifold to a curve in Rn. This composition effectively relocates the curve from the manifold into the Euclidean space, allowing us to perform calculus on it. Once the curve is mapped to Euclidean space, we can finally compute the velocity vector at point P by taking the derivative of phi composed with gamma of t with respect to t. This derivative gives the velocity vector of the curve at the point P equals to gamma of t0. but now expressed in terms of the local coordinates. All of this was to introduce tangent vectors as velocities of curves passing through a point P on the manifold. But this is not enough for practical analysis, because a single tangent vector is just one direction of movement at P. But instead, we need to describe all possible directions at P, which forms the tangent space of the manifold M at point P.
If you're enjoying this video, please don't forget to like it and to subscribe to the channel.
To study the manifold globally, so not only in one specific point, we also need a way to compare different tangent spaces at different points or under different charts. This is where the idea of a basis comes in.
So we want to be able to do analysis between points and charts, not just a single point or chart. In order to do so, we need to introduce an arbitrary function f, an entirely different field called a scalar field. What it does is assign scalars to each point on M. Scalars are much like vectors, except they don't have a direction. It's much like velocity versus temperature, for example. It's like if we pick a point P on the manifold and apply f, we will therefore assign it a number or a scalar. Just for the sake of intuition, let's say we're assigning temperature. Again, just as an example.
Now, say we want to find the rate of change of our function f as we walk along our curve gamma of t. We want to look at a new definition of velocity relative to this test function at our point P on the manifold. But here's a really fun trick we can do by introducing phi and its inverse. It's a trick because it doesn't really do anything. It's just like adding 0 or multiplying by 1. Because this introduction is quote-unquote harmless, we can therefore put it like this. Now, we introduce the chain rule, which we won't go into detail, but if you want to know more, let us know in the comment section below. Which brings us to here, since P equals gamma of t0. With the left part being the basis for component I, and the right part the velocity of component I with respect to phi. Here's something that is a little weird. We're going to rewrite the basis like this. We see that phi disappeared, but it's just a convention, and phi is specified by xi.
And what is the f? It was an arbitrary test function. We just needed it in the calculations to get us where we got to. You can pick literally any differentiable function f. It doesn't really matter what it is. We only needed it to define the basis of the tangent space. So it was so arbitrary that we can actually get rid of it now. So for every tangent vector v in TPM, we have this. It turns out the basis is actually a set of differential operators, not the actual vectors on the test function f, which make up a vector space. A vector space doesn't need to be our usual Euclidean vectors. They can be anything that satisfies the vector space properties, including differential operators.
It is important to remember that there is a chart behind it, or under different charts. So we found a basis to the tangent space at a specific point. And since we want to do it for every point in the manifold, the next logical step would be to compare different tangent vectors in different tangent space at different points in the manifold M. So if you're curious to know more, leave us a comment. Also, do not forget that we include a PDF, which is like a summary of everything we see in the video. This way you guys can study by yourself at home. And remember, that's the only way to really learn math, by understanding each step, each detail, and then trying to reproduce everything independently by yourself. I guarantee you that it's going to be very beneficial. So download the PDF link in the description below. Tangent spaces allow us to zoom in into the manifold and somehow do calculus there, even if the space itself is not flat. But the tangent space is flat. We use charts and curves so that we can transform these abstract notions into the calculus we're used to. This is a crucial step, because once we learn how to define vectors on a manifold, we're ready to explore how they interact with each other and how they change, which will lead us to talk about curvature in a more precise and mathematical way. Chapter 5. Schwarzschild spacetime. In this chapter, we're skipping way ahead of what you can take, at least as the mathematics necessary to understand general relativity. But actually, we're doing this intentionally. because I want you to not only learn the details of everything we're talking about so far, but also to understand where we're heading to. So don't worry if you don't understand everything in this chapter. And remember the wise words of mathematician John von Neumann. In mathematics, you don't understand things, you just get used to them. This is definitely one of the most important equations you will ever study in your life. The left side represents the curvature of the manifold, and the right side the distribution of matter in it. It is called Einstein's equation, or Einstein field equations, since there is more than one. And this manifold is often described as the space-time around us. You don't need to know its precise definition for this video, but just to give you the intuition behind it, think of a manifold as a shape or surface that can be stretched and bent, but looks flat if you zoom in close enough. For example, the surface of the Earth is a curved 2D manifold, but it feels flat when you are standing on it. In this context, the space-time is a 4D manifold that describes the stage where everything happens. From the mathematics point of view, general relativity is just a combination of differential geometry, tensor calculus, topology, algebraic geometry, Lie groups and Lie algebras, functional analysis, and partial differential equations. I know, it's a lot. But here we'll focus on a specific solution of this nonlinear partial differential equation, namely the Schwarzschild solution.
A solution of this partial differential equation is a metric tensor that defines the geometry of the manifold or spacetime. A differential equation can be seen in a very simplistic way as a soda machine. You give it an input, usually money, or a strong kick, depending on your mood, and it spits out an output, usually the desired soda can, depending on its mood. A partial differential equation, like the one we are interested in, works in a similar way. The input in this case is one of its correct mathematical solutions, and the output might be a geometrical interpretation of the result in the manifold we are working with. In the specific case of general relativity, this manifold is 4-dimensional, such that 3 dimensions represent space and 1 represents time. So each input or solution of Einstein's equation gives a different output, or geometry of spacetime. The Schwarzschild solution is just one of these possible inputs, the very first one that was discovered. We won't prove that this metric is actually the solution of Einstein field equations, because the calculations are really long, but we will analyze and interpret each term. Before anything though, let's see the assumptions used by Schwarzschild to find this specific solution. The first, spherical symmetry. The manifold is assumed to be invariant under the group of rotations SO3. Group of actions SO3 is the set of all possible rotations in 3D space. Imagine spinning a ball around any axis. SO3 describes all the ways you can do that without changing the ball's size or shape. This means that the metric is unchanged under transformations, corresponding to any rotation in 3D. The metric coefficients g mu nu can depend only on the radial coordinate r, in other words, the distance from the center, except for the angular part, which includes the dependence on sine squared theta, arising from the spherical coordinate system. If you're enjoying this video, don't forget to like it and to subscribe to the channel.
The second assumption is no rotation. To talk about this one, we need to define angular momentum first. This is the spin of an object. A spinning top or a rotating planet has angular momentum. It is the way the object keeps spinning unless something stops it. In this metric, the angular momentum is 0, which is illustrated in the fact that all the terms not in the diagonal of the matrix are 0, just as gt phi, for example. If this was not the case, there would be something called frame dragging, which by the way is present in the famous Kerr solution. We'll talk more about it later on. The third assumption is radial symmetry. This is a consequence of the spherical symmetry. It means that the radial part of the metric depends only on the magnitude of r, not on direction. The fourth is vacuum. This one may sound a little weird at first, since vacuum is a situation where there is no matter involved. However, the spherical geometry of our manifold is the direct consequence of the spherical geometry of a body at its center, like a planet or a star. So it is important to notice that this metric solution describes only the curvature outside of the body, not with respect to a point in its interior. Mathematically, the energy momentum tensor T mu nu is zero everywhere. This condition simplifies the Einstein field equations a lot. In terms of differential geometry, we say that spacetime is Ricci flat. And the last assumption is no electrical charge. As a consequence, the metric G mu nu remains purely gravitational. And there is no electromagnetic field tensor F mu nu.
So let us see once again the full version of the Schwarzschild solution. It's important to understand that in differential geometry, the metric's components determine the distances, angles, and causal structures. When the metric tensor G mu nu has only diagonal terms, just like the Schwarzschild solution, it implies certain symmetries and simplifications, both mathematically and physically. Cases with non-zero off-diagonal terms reflect more complex phenomena, such as rotation, non-static spacetimes, or the presence of additional fields, like an electromagnetic field, for example. The fact that the Schwarzschild solution is a diagonal metric indicates that the coordinate basis vectors are orthogonal to each other. Another alternative metric that satisfies Einstein field equations and that is diagonal is the Friedmann-Lemaître-Robertson-Walken metric for cosmology, which assumes a homogeneous and isotropic universe. If we had non-zero off-diagonal terms, the coordinate basis vectors would no longer be orthogonal to each other. For example, the Kerr solution has a non-zero term, which introduces coupling between time and angular components. The Kerr metric describes a rotating black hole. The discovery of what we now know as the Schwarzschild solution was very surprising at the time because the Einstein field equations are a set of complex, highly nonlinear partial differential equations. Just to illustrate how complex these equations are, notice the Matryoshka-Dolls effect of trying to express it just in terms of the metric tensor G mu nu.
Karl Schwarzschild discovered an exact solution just a few months after Einstein published the final form of his equations. The solution revealed a singularity at the radius 2gm divided by c squared, which later became known as the Schwarzschild radius. A singularity is a point where something breaks down completely, like dividing by zero in mathematics. In spacetime, a singularity is a place where gravity becomes so strong that the usual rules of physics stop working. At the time, the interpretation of this singularity was not understood. The idea that space-time could end, or that of a region where nothing, not even light, could escape it, was just weird. Today, that's what we call a black hole. If you want to know more about it, check out the PDF link in the description below. There we added many more things in more detail so that you guys can learn. In conclusion, if Einstein's field equations looked intimidating before, now you understand why. Even trying to write them out in terms of the metric G opens up a chain of expressions that just makes everything huge. Ricci tensor, Christoffel symbols, scalar curvatures, and so on. It's like opening a Matryoshka doll, one after the other. But out of all these mathematical objects, the one I want you to focus the most and pay the most attention to is the metric tensor G. Your goal is to find this guy, because this guy is exactly the solution of Einstein's equations. And as a consequence, it will provide the shape of space-time according to the problem you're studying. The Schwarzschild solution is just one metric out of all the possibilities that there are, probably infinite possibilities. It's one of the most important ones, by the way. But remember that solving Einstein's equations means finding a metric, one that will give you a shape of space-time. Chapter 6. What curvature really is. Most people think of curvature as something you can see, like the curve of a hill or a bent piece of metal. But in mathematics and physics, especially in differential geometry and general relativity, curvature isn't something you can always see, but it's something that you can detect or measure, even without ever leaving the surface or the space you are on. In this chapter, we'll learn the concept of an intrinsic curvature. And that's the kind of curvature you measure from inside of the space, which is something super important in the context here. We'll do it using triangles, angles, straight lines, circles, and so on. Newton was the one who found out that everything attracts everything else with a force inversely proportional to the square of the distance. Einstein had a different interpretation of gravity. Space and time are not as rigid as Newton thought. They are distorted near massive objects. And the curvature can be perceived more clearly when dealing with heavy masses. It is this curvature of space-time that gives the effect that we call gravity. Mathematically, the scenario changed as well. Gravity is not a force anymore, but merely the distortion of space-time around the massive object. There are three things involved here. One is the effect of gravity. Another is the idea of space-time. The third involves the idea of curvature. We'll simplify things in the beginning by not talking about gravity and leaving out the time. So in the beginning, we'll just focus on curvature. Now, even that much turns out to be very hard in 3 dimensions. So we'll first reduce the problem to a curved space in 2 dimensions. In order to understand this idea of curved space in 2 dimensions, you need to put yourself in the shoes of a creature that lives in such a space. One of my favorite books that helped me to appreciate dimensions in math and physics and also improved my spatial intuition when navigating high dimensions is Flatland, A Romance in Many Dimensions by Edwin Abbott. Let me give you a taste of it. Imagine a very weird bug with no eyes who lives on a plane. He can move only on the plane, and he has no way of knowing if there is a whole world outside of the plane. This bug is 2-dimensional. He has no thickness, no height. If you take the sheet of paper where it lives and look at it from the side, you see the bug just as a straight line. You may find yourself having a hard time being empathetic with this being. I mean, what a stupid bug. Why can't it just literally look up and see that his world is actually just a section of a much larger 3-dimensional world? The world where we observe him from above. Or at least he could imagine it, right? Well, actually, we live in a 3-dimensional world, and we usually have no imagination about going out of these 3 dimensions to another direction. I mean, nothing guarantees us that there are no other dimensions out there, other directions, beyond the 3 dimensions of space and 1 of time. As far as we know, there are only 4. At least that's what physics tells us. But in the mathematical world, 10, 100, or even infinite dimensions are as real as the 3 dimensions we're used to. Another example of a bug living in 2 dimensions is one that lives on a sphere. He can move around on the surface of the sphere, but just as before, he cannot look up, or down, or out. Also, because up, down, and out do not exist in his 2-dimensional world.
Now we consider a third kind of bug. This is also a bug that lives on a plane, like the first one, but this time with a little caveat. This plane is a disk, with different temperatures at different places. It is cold in the center and heats up gradually as one moves away from it. In other words, with a non-constant scalar field defined on its domain. Also, the bug and any objects in it, including the rulers he uses now, and then to measure distances, are composed of the same material that expands when heated up and contracts when cooled down. Everything is longer in the hot places than it is in the cold places. And everything has the same coefficient of expansion. But we forgot to tell you that these are no ordinary bugs. They're actually very smart, and they want to study geometry. They draw lines, make rulers, and measure lengths. One of the simplest ideas they learned is how to draw straight lines in their respective spaces. A straight line is defined as the shortest distance between 2 points. The first bug makes beautiful straight lines. But what about the bug on the sphere? He draws a straight line as the shortest distance for him between 2 points. It looks like a curve to us because we have the privilege of a 3rd dimension, which is actually an arc of a great circle. But for him, 2 is the maximal number of dimensions that exist. All he actually knows is that if he tries any other path in his world, it's always longer than his straight line. It's just his empirical knowledge. The third bug will also draw straight lines that looked curved to us. The shortest distance between the points A and B is a curve. How come? Because when his line curves out toward the warmer parts of his plate, the rulers get longer. They expand, but only from our point of view, of course. And thus it takes fewer sticks laid end to end to get from A to B. For the bug though, the line is perfectly straight. Now let's see what the rest of their geometries look like. Let's assume that all the bugs learn how to make the lines intersect at right angles. Then the first bug, in the normal plane, finds an interesting fact. If he starts at point A and makes a line 100 inches long, then makes a right angle and marks off another 100 inches, then makes another right angle and goes another 100 inches, and then finally makes a third right angle and a fourth line 100 inches long, he ends up right at the starting point. He calls it a postulate in geometry. More specifically, a postulate in his geometry. Let's call this bug Euclidicus. Then Euclidicus discovers another interesting fact. If he makes a triangle, which is just 3 straight lines connected at the endpoints, the sum of the angles is equal to 180 degrees. Right after that, Euclidicus makes a circle. He started at a fixed point and rushed off on straight lines in many directions. Then he laid out a lot of dots that are all the same distance from that original point.
One day, Euclidicus decides to measure the distance around many of the circles he drew, just out of curiosity. He finds an interesting relation. The distance c around the circle is always the same number times the radius r, approximately 6.283, and so on. In other words, 2 pi, no matter the size of the circle. What about the other bugs? Well, the bug on the sphere tried to make a square, but ran into some technical difficulties. He started at a point A and drew what he calls a straight line in any direction. Then, he turns 90 degrees and makes another straight line with the same length. Continuing this process will not allow him to close the square, ending exactly where he started, at point A. If you do not believe me, get yourself a sphere and try it out.
If you're enjoying this video, don't forget to like it and to subscribe to the channel.
The bug in the plate will have a similar problem, but for a different reason. Since his rulers expand or contract depending on the direction of his motion, if going from hot to cold or from cold to hot, he will not be able to close the square. The point is to understand here that just by geometrical measurements, the second and the third bugs could quickly discover that there was something weird about their spaces. And this weirdness is related to the concept of curvature. A curved space is a space where its geometry is not what we expect it to be on a plane. The last 2 bugs experience geometries that are characteristic of curved spaces. In other words, the rulers of Euclidean geometry fail. And you don't need to be able to lift yourself out of the surface towards the third dimension in order to find out that the world that you live in is curved. You do not need to go around the globe in order to understand that you live on a ball. All you need to do is to try to draw a square. If the square is small, you'll need a lot of accuracy in order to notice that the process actually failed. But if the square is large enough, you can easily see that. Let's see the case of a triangle now. The bug on the sphere can construct a triangle that has 3 right angles. So weird. The bug can start at the North Pole and make a straight line all the way down to the equator. Then he turns 90 degrees and make another straight line with the same length. Then again. And there we go. A triangle with 3 right angles. Actually, all triangles he draws will have the sum of its angles greater than 180 degrees. If his buddy Euclidicus told him that it was supposed to add up to 180 degrees, he would probably laugh. And the bug on the plate would also laugh at this statement, but for a different reason. What about circles? How do the other bugs interpret circles in their spaces? The bug on the sphere makes a circle using the same procedure as we've seen before. After measuring the circumference, he finds out that it is less than 2 pi times r. For us, who are extremely privileged observers, it is obvious that a circle with this radius r would have a greater circumference in comparison to the one made by the poor two-dimensional bug. Actually, we know that what the bug calls radius is a curve that is longer than what we call radius. Now this bug talks to his friend Euclidicus, who teaches him a cool way of predicting the radius of his circle by dividing the circumference c by 2 pi. Then, in order to check if Euclidicus was legit, the bug on the sphere decides to measure the radius by himself. He would find out that the measured radius was actually larger than the predicted one. This difference is what he called the excess radius, and he went on to win the Fields Medal for it. It turns out that the excess radius is related to the size of the circle. Meanwhile, the bug in the plate was feeling a little jealous. So he decided that he would pursue his own geometric postulates, because his space is way cooler anyway, relatively speaking. He drew a circle centered at the cold spot, and what he calls radius are actually curves for us. When he measures the circumference, he too finds out that the measured radius is longer than the predicted radius. In other words, c over 2 pi. He shouts, "Eureka!" and discovers what he calls the surplus radius. He tried to publish a paper about it, but someone already beat him to it. A curved space is one in which these kinds of errors occur. The sum of the angles of a triangle is different from 180 degrees. The circumference of a circle divided by 2 pi is not equal to the radius, and the rule for making a square does not produce a closed figure. You can think of others. Let us know in the comment section below your thoughts about it. We're curious to know about other ways of noticing curvature on a space without mentioning an external dimension.
These are just two examples of curved spaces. In the plate, if you choose the right temperature variation as a function of distance, so the right scalar field, then its geometry can be identical to the sphere. In other words, while being a bug living in such a space, you wouldn't be able to tell if you lived on a sphere or on a plate with different temperatures. Crazy, right? There are, of course, different kinds of geometry. What about a bug living on a pear? At some points, this space presents sharp curvatures. At others, it's almost flat. Triangles here would also have the sum of their angles greater than 180 degrees, no matter where you draw it. A question that may come to your mind is it possible to find a triangle in a space with the sum of its angles being less than 180 degrees? Yes, but not in the spaces we've seen so far. The sum of the angles of a triangle is greater than 180 degrees on a positively curved, closed surface, such as a sphere and a pear. Conversely, it is less than 180 degrees on a negatively curved, open surface, such as a hyperbolic plane. Imagine a saddle, for example. Now, draw a circle on the surface. This is called the locus of all points at the same distance from the center. Its circumference is actually larger than you would expect from calculating 2 pi times r. In this case, the predicted radius would be less than the measure radius. As a consequence, the excess radius would be negative. General relativity predicts 3 possible geometries for the universe, determined by the density parameter omega 0, which compares the actual density of the universe to a critical density. If omega 0 is greater than 1, the universe has positive curvature. This type of universe is finite and closed. So if you traveled far enough in one direction, you would eventually return to your starting point. Over time, the gravitational pull of matter would cause the expansion of such a universe to stop and reverse direction, which would lead to a catastrophic collapse known as the Big Crunch. On the other hand, if omega 0 equals to 1, the universe is flat with zero curvature. And thus the familiar rules of Euclidean geometry can be used to study its structure on large scales. This flat universe would expand forever, but the rate of expansion would asymptotically approach zero as gravitational forces gradually slow the outward motion. If omega 0 is less than 1, the universe has negative curvature and is infinite. In this case, the universe would also expand forever, but at an ever-increasing rate, because of the insufficient gravitational pull to counteract the initial expansion. Physicists are still uncertain about which model describes our cosmos. The problem is that it's really hard to precisely measure the density of matter and energy in the universe, especially dark energy, which is what drives the acceleration of the expansion.
Going back to our bugs, we noticed that from the definition of curvature that we've seen so far, a cylinder is not curved. If a bug lives on a cylinder, then triangles, circles, and squares would all have the same behavior they have on a plane. I mean, all you need to do is unroll the cylinder onto a plane, and you will find that out. Therefore, there is no way for a bug living on a cylinder to discover that his space is not a plane, unless he goes all the way around it, because then he would notice that he came back to the starting point after moving on what he calls a straight line. So, in our technical sense, we consider that his space is not curved. What we're really talking about, though, is the concept of intrinsic curvature, which is crucial for the whole understanding of differential geometry, and as a consequence of general relativity. If you want to know more about it, check out the PDF link in the description below.
This video was inspired by this book.
To conclude, what looks just like geometry, so triangles, angles, circles, straight lines, turns out to be something much deeper, which is the curvature of space itself. And in Einstein's theory, that curvature is gravity, which produces motion and the shape of the universe. Chapter 7. The Mathematics of Minkowski Spacetime. Could we describe spacetime with a certain geometry that naturally encodes the speed of light and some of its properties, as well as the concept and the notion of causality? In this chapter, we'll see Minkowski geometry, which is actually the basis of special relativity, but learning it will help you to understand general relativity. We're going to make some very simple assumptions about the speed of light, and we'll see how naturally the consequence will be Minkowski geometry, specifically in the 4D manifold that we use to model spacetime. This graph represents space as a 2D xy plane, and the vertical axis is the speed of light c times the time t. Usually this axis is used to represent just time, and this way an object at rest in space would move in a straight line in spacetime. Similarly, a planet orbiting the Sun would draw a spiral when moving throughout spacetime. But here, we added the c in front of t, and one of the reasons is because this way all axes have the same unit of measurement, let's say meters for example. Another reason for using ct instead of t is because this choice will give us a very cool symmetry that we'll see later on. This is going to be extremely useful, and we'll see this symmetry through the following example. Imagine we have a point moving at the speed of light away from the origin. This point will trace a spatial distance of 3 times 10 to the power of 8 meters after 1 second. Similarly, the distance traveled in the vertical axis would be 3 times 10 to the power of 8 meters per second times 1 second. Now we do the same for 2 seconds, and we get the point ctx as 6 times 10 to the power of 8 and 6 times 10 to the power of 8. In other words, this specific choice of axis, ct, allows us to trace a line with a 45-degree angle that defines the path of any point moving at the maximum possible speed, in other words, the speed of light.
Anything faster than the speed of light will trace a line, or a curve with tangent line, that has inclination less than 45 degrees. This can be intuitively understood through the fact that the body moves spatial distances that are longer than c-time distances in the spacetime diagram. Anything slower than the speed of light will trace a line, or a curve with tangent line, that has inclination greater than 45 degrees. This is not only true for points traveling to the right in x and to the right in y, but also to the left in x and to the left in y, or any permutations. This creates a cone, such that everything that is inside of the cone is said to be causally connected to the origin, because it can be reached with a speed v less than or equal to c. anything that is located outside of the cone is said to be causally disconnected to the origin, because it could be reached only with a speed v greater than c. This is not only true for future events, but for past events as well. The elegance of Minkowski geometry emerges from the fact that all of it, and plus a few other things that we'll see in a bit, come from just three simple assumptions. In this spacetime diagram, there are three kinds of regions. The existence of these three kinds of regions is a direct and exclusive consequence of the following assumptions: that the speed of light is finite, that the speed of light is constant, and that the speed of light is the maximum limit speed in the universe. These three regions are s squared greater than 0, s squared equal to 0, and s squared less than 0. The letter s here represents space-time distance, not spatial distance d.
These three regions are separated by the cone-shaped figure that we just talked about. S squared can be measured using the Pythagorean theorem. Of course, here we are considering space to be two-dimensional, but the physically correct assumption would involve a xyz structure, plus the ct axis. It is reasonable that the distance squared from 2 points is positive. So s squared is positive in space-time. Which means that traveling at any speed v less than c, I can get to the desired point. It is not reasonable, though, that distance squared, so s squared, is 0 in space-time when using Euclidean geometry, other than the case in which time is frozen, like a picture. And when using Euclidean geometry, we never have that a distance squared in spacetime is negative. So s squared less than 0. It's a contradiction. So Euclidean geometry does not accommodate regions s squared equals 0 and s squared less than 0. The question is, should we change from Euclidean geometry to some sort of alternative geometry? Or should we abandon this understanding of three regions of spacetime? Maybe only s squared positive is possible, and the other regions with s squared equals 0 or s squared negative are just nonsense. Well, again, imagine a point moving at the speed of light. The amount of time passed and the variation of spatial position are clearly not 0. Delta t is not 0, and delta d is not 0. Indeed, if v equals c, we have this. Using Euclidean geometry and this expression, we measure the space-time distance s. S squared is c squared times delta t squared plus delta d squared, reminding you that delta d squared is x squared plus y squared plus z squared. And using this equation, we find out that s squared can be written as 2 times c squared times delta t squared, which is different from 0, since the time interval is not 0. So the Euclidean geometry implies that s squared equals 0 is impossible. Similarly, in order to reach region s squared negative, we need a velocity v that is greater than c. This time, the speed of light c is less than delta d over delta t, which implies that delta d is greater than c times delta t. Using Euclidean geometry and this expression, we can measure the spacetime distance s. S squared equals c squared delta t squared plus delta d squared. And using a very similar reasoning as before, we find that s squared now needs to be greater than 2c squared times delta t squared, which is a positive quantity. So we just found out that s squared cannot be negative. And therefore, Euclidean geometry implies that s squared less than 0 is impossible. In conclusion, Euclidean geometry allows us to describe points in spacetime only inside of the cone, with s squared positive. It does not accommodate for the description of the other two regions, s squared equals 0 and s squared negative. We need another metric. So, a way of measuring spacetime distance s that will cover all three regions. A metric can be thought of as a special ruler that will be used to measure spacetime distances. This is not like your regular Euclidean ruler. Let's derive this metric. So first, s squared positive. The velocity v is less than the speed of light c, which implies that delta d over delta t is less than c. In other words, delta d is less than c times delta t. But this implies that x squared plus y squared plus z squared is less than c squared times t squared. It is okay to use Euclidean metric for calculating spatial distances. There is no contradiction here. But when it comes to spacetime distance, it turns out that this will be our new s squared, or metric, rather than the old unsatisfactory Euclidean metric. So the definition of s squared that we are going to use now is c squared t squared minus x squared minus y squared minus z squared. Let's see how this metric, which is non-Euclidean, behaves for the other two regions. So s squared equals 0 now. V equals c now. So delta d can be written as c times delta t. Working on the math here, in a very similar way as before, we can find indeed that s squared equals 0, just as desired. And finally, s squared less than 0. Now v is greater than the speed of light c, which implies that delta d is greater than c times delta t. And working on the math here again, we can find that s squared is indeed less than 0, just as we wanted. So this formula for s squared works perfectly. It describes all regions. We found our metric, the Minkowski metric. The Minkowski metric can also be seen as a matrix transformation. All we have to do is write it as a multiplication of a vector times a matrix times another vector. And we see that we can recover the original metric by performing the calculations. So this is the Minkowski metric written as a matrix transformation. It's usually denoted as eta. Mu nu represent just the rows and columns, 0, 1, 2, and 3. So 4, because we're describing a 4-dimensional spacetime.
This matrix transformation bridges classical mechanics or Euclidean geometry and special relativity, so Minkowski geometry. And it does so by reconstructing spacetime. At this point, you'll need to change the way your intuition works. This is valid if you're doing either mathematics or physics. If you're enjoying this video, don't forget to like it and subscribe to the channel. Let's use linear algebra in order to understand this new geometry. One of the first things that come to mind when we find a new matrix transformation is to compute its eigenvectors and eigenvalues. We want to find the eigenvalues and eigenvectors of the following matrix. In order to accomplish that, we need to solve the following equation. For a detailed explanation of how we got to these eigenvalues and eigenvectors, check out the PDF link in the description. This eigenvector represents the c-time direction. Any vector along this direction is preserved. So with eigenvalue lambda equals to 1, under transformations that respect this metric. For the eigenvalues -1, which are threefold degenerate, we have these eigenvectors. These eigenvectors represent the spatial directions. Any vector along these directions flips signs, so with eigenvalues lambda equals -1, under this kind of transformation. The Minkowski matrix transformation is interesting, but again, it only serves the purpose of opening the door to Minkowski geometry or special relativity in physics. What we're actually looking for is a transformation that preserves the most fundamental property of this new geometry, which is the space-time interval S, regardless of the speed v of the observer. In other words, we want to find a matrix that satisfies this equation. Such a matrix lambda would ensure that the Minkowski matrix eta remains unchanged. guaranteeing that spacetime intervals are preserved under this transformation. But what kind of transformation could achieve this? We can do some math to find out.
This mysterious matrix acts on all vectors of the form Ct, x, y, z in spacetime. For simplicity, let's assume that the point moves with a velocity v only in the x direction, so it has a component vx and the other two are 0. This implies that the matrix lambda must be a linear transformation that mixes Ct and x components while leaving y and z unchanged. Our goal is to find the values of a, b, c, and d. Plugging this general matrix into our equation and working on the math here, again, check out the details in the PDF link, we find these values for the variables a, b, c, and d. A and d are both the hyperbolic cosine of an angle theta, and c and b are both the hyperbolic sine of an angle theta, where theta here is the angle of inclination of the tilt of the new c-time and space axis after the transformation. We'll clearly see in a bit how and why this tilting happens. By the way, this angle theta is usually called rapidity. A straight world line, so a path in the spacetime diagram, represents constant velocity. The slope of this world line is delta x over c delta t, so v over c, which measures how much space it covers per unit of c time. Since Minkowski space follows hyperbolic geometry, the natural angle measure for this inclination is given by the hyperbolic tangent. So we have that the hyperbolic tangent of theta is v over c. Using this fact, we can work on the math here that you can find in the PDF link. And we find out that the values a, b, c, and d in terms of the velocity of motion v and the speed of light c are these. Therefore, the matrix transformation that we are looking for is this one. Or, more compactly, we can call beta v over c and gamma the term 1 over the square root of 1 minus v squared over c squared. And then we write this matrix this way. This is the Lorentz transformation matrix, or the Lorentz boost, and gamma is referred to as the Lorentz factor. This matrix is important because it describes how space-time coordinates transform between observers moving with a constant velocity relative to each other. It preserves the space-time interval s squared, defined as c squared, t squared, minus x squared, minus y squared, minus z squared. It ensures that the speed of light remains constant, and it keeps the fundamental structure of Minkowski spacetime unchanged. Now, this is not the most general version of a Lorentz boost, because we assumed motion only in the x direction. If we allow the boost to occur in any random direction, with components vx, vy, vz, then the generalized Lorentz transformation matrix looks like this. Yeah, it's huge, I know.
And by the way, even this is not the most generalized version ever, because it accounts only for translations, but not for rotations. The most general version is even more complicated. Of course, this generalized matrix is obtained by combining the boosts in the three directions, but not in a linear way. Check out the PDF in the description below to see a really cool way of deriving this general result. The next logical step would be to calculate the eigenvalues and eigenvectors of this matrix, since they give us information about what directions are preserved in the transformation and by how much its eigenvectors are stretched or compressed. In order to do so, we will first calculate them for the standard Lorentz boost in the x direction, and then we will extend the results for the four-dimensional Minkowski spacetime. That's the matrix we'll work with.
After solving the appropriate equations, we find the following eigenvectors with their respective eigenvalues. For the first eigenvalue, we find the eigenvector 1, minus 1. For the second eigenvalue, we get the vector 1, 1. Graphing these results, we see that one of the vectors gets contracted, while the other gets stretched. All of it takes place along these two great lines, which, by the way, form the light cone. As a more concrete example, imagine that this is a Lorentz boost such that the point particle that we're studying moves at 90% of the speed of light, so v is 0.9 c. Notice that the velocity of a stationary observer with respect to the particle moving at 90% of the speed of light will be a negative number. In this situation, since they are moving away from each other with velocity v, we'll consider the velocity measured by the stationary observer to be negative v. Using the velocity v, we calculated beta as minus 0.9. Check the PDF. The Lorentz factor is about 2.294. One of the eigenvalues is approximately 0.229, with its eigenvector being transformed into the vector 0.229, negative 0.229. The other eigenvalue is around 4.358, and its respective eigenvector is transformed into the vector 4.358, 4.358. Graphically, we start with the eigenvectors 1 minus 1 and 1, 1, and they get scaled by their respective factors. Interesting, we're slowly drawing the new diagram we get after the transformation. Let's see what happens with the CT and x-axis now. So the CT axis is defined by the vector 1, 0. After performing the transformation, we find the vector gamma that multiplies 1 minus beta. The x-axis is defined by the vector 0, 1. And after applying the transformation, we get gamma times the vector minus beta 1. So the question here is, are these two vectors orthogonal to each other? Let's find it out by performing their dot product. If it results in 0, then they are still orthogonal even after the transformation. Performing the dot product, we find minus 2 gamma squared beta. If v equals 0, so if the velocity is 0, then this results in 0. When v is different from 0, so for example, in our case here, with a negative velocity, the dot product results in a negative number, which implies that the axes ct prime and x prime after the transformation are not orthogonal anymore. Now, performing the Lorentz boost, for many points in the grid of the plane, we get a very good grasp of the dynamics of the motion. This is clearly a hyperbolic spacetime. Of course, we can extend it to 4 dimensions, ct, x, y, and z, describing the Minkowski spacetime. The formula of a hyperbola can be derived from the Minkowski metric, where 1 is the length of the axis here. That's just the definition of a hyperbola. We cannot draw the 4-dimensional case, just a 3-dimensional version of it. But you can use your imagination to try to grasp the idea of extending this diagram to 4 dimensions. And this is Minkowski geometry. So from just a few assumptions about the speed of light, we've built an entire new geometry, which is different from the usual Euclidean one. It's not exactly flat. It is a hyperbolic geometry called Minkowski geometry. Chapter 8. Riemannian Manifolds. We've already seen what a manifold is. Intuitively, it's just a space that when you zoom in, when you look up close, it looks like a flat Euclidean space, even though it may have curvature globally. But now we need a more powerful type of manifold with more structure. And this is a Riemannian manifold. In general relativity, spacetime isn't modeled as a Riemannian manifold, but actually as a pseudo-Riemannian manifold. So we need more than just smooth manifolds now. We need a way to measure things. So lengths, angles, distances, curvature, and so on. And this new structure is going to be a metric, a Riemannian metric. In this chapter, we'll see many examples, but try to understand why this is important. So the motivation behind it. And we'll also touch on some points about topology here. But don't worry, nothing too complicated. This is a space that looks very simple, but it has some extremely powerful properties. The first one will be expressed through the following illustration. Imagine you are an ant. walking around a giant, weirdly shaped object. Say the surface of a donut, or a globe, or something funkier. Even if the shape is complex and curvy, up close, it always feels like you are walking on a flat, ordinary two-dimensional space. A manifold is just like that, where every small patch looks like flat space if you zoom in enough. Now, C infinity means it is smooth. You can do calculus on it. You can take derivatives as many times as you like, and everything behaves nicely. No sharp corners, no jumps. Think of this saying that you can draw curves and do math on them without any weird breaks. Another important property is that the space is Hausdorff. This just means you can separate any two different points with their own bubble. So, open sets that don't overlap. In a regular space, like the room you're probably in, if you pick 2 points, you can create a little ball around each such that they don't touch. That's Hausdorff. So it avoids weird spaces where points cling together in strange ways. In order to appreciate this property, which we very often take for granted, let's see a counterexample of such a weird space, so a non-Hausdorff space. This example is called the two touching planes. Imagine 2 copies of the plane R2, say P1 and P2. Now glue them together along everything except the origin. That means all points x and y different from the origin in P1 and P2 are identified. They are the same. But the origin in each plane, so 0, 0, 1 and 0, 0, 2, are kept as separate points. Now you have 2 origins, but everything else is merged into a single copy. Let's try to create 2 open disks, or neighborhoods, around 0, 0, 1 and another around 0, 0, 2. The problem is, no matter how small the disks are, they will always share all the same points except the origin, so the disks always overlap. This makes it impossible to separate the origins of the first plane from the origin of the second plane with non-overlapping open sets. In other words, the space is not Hausdorff.
Every Riemannian manifold must be Hausdorff, so you have to be able to separate distinct points using open neighborhoods. Another property that gets many people confused, but is super important, is the following. Think of a space, like the real plane, as a huge Lego world. The open sets are the Lego bricks that you use to build any shape or structure, so any neighborhood. But just like in Lego, you don't need every possible shape. You just need a collection of small pieces that you can combine. That collection is the intuition behind a basis in a topological space. A basis is a special collection of open sets that acts like the building blocks of spaces. Now, we want the set of basic building blocks, so open sets, to be countable. That means you can make a list of them. Even if it's infinite, the list behaves like counting 1, 2, 3, 4, and so on. Anyway, this property is better expressed by saying that the space is second countable. In other words, there exists a countable list of open sets, such that any open set in the space can be made by gluing some of them together. Why does it matter? Being second countable ensures that the space is not too big, in a topological sense. Also, it guarantees that you can use sequences instead of more complicated tools. The classic example of a second countable space is Rn, the real space in n dimensions, even though the set of real numbers itself is uncountable. You can make a countable collection, so a list of all open balls with rational center coordinates and rational radius. This is possible because, despite the fact that the set rational numbers is dense, it is countable. Of course, this depends not only on the space itself, but mainly on the kind of topology that we chose. So, the definition of open sets that we're using. If you're enjoying this video, don't forget to like it and to subscribe to the channel.
A counterexample would be the set of real numbers with a discrete topology, tau. This topology defines open sets as subsets of the real numbers, with only one element, called singletons. This is certainly not countable. Because if it were, then the real numbers themselves would be countable as well. And we know that the set of real numbers is uncountable. So these are the properties we've seen so far. The space is locally Euclidean, so a manifold. Smooth, you can do calculus in it, so it's C-infinity. Well-behaved, in the sense that no points stuck together in weird ways, so it is Hausdorff. And the space is not too big or too messy. In other words, it is second countable. So far, this is the precise definition of a smooth manifold. Remark: in differential geometry, the definition of a manifold assumes the space to be Hausdorff and second countable. However, in order to build a Riemannian manifold, we need one more thing: a Euclidean inner product on each tangent space of the manifold. But first of all, what is an inner product? It's a mathematical tool that allows you to measure lengths of vectors, angles between them, and say how much one vector points in the direction of another. It's like giving your space a way to talk about geometry, even if it's curved or abstract. You should think of the inner product as a directional ruler. It doesn't just tell you how long something is, it also tells you how aligned two things are. Imagine two vectors in space. If they point in the same direction, it produces a large positive inner product. If they are at 90-degree angle, the inner product is 0. If they point in opposite directions, the inner product is very negative. Let's introduce a little bit more rigor to it, and we're going to do it through a specific example. The two vectors are v with coordinates x1, y1, and w with coordinates x2, y2. Then the standard inner product, which in this particular case is also called dot product, is x1 times x2 plus y1 times y2, which implies that the length of the vector v can be calculated this way. So the square root of x squared plus y squared. It's just the Pythagorean theorem. And the angle formed between these two vectors is calculated using the cosine formula. So the dot product divided by the multiplication of the lengths of each vector.
But in a Riemann manifold, we also require the inner product to be Euclidean. So three conditions must be satisfied. First is that it is symmetric. This means that projecting the first vector's length onto the second or vice versa produces the same result. Second, it is bilinear. In words, if you scale one vector by A and another by B, then add them and project the result onto a third vector Z, you get the same outcome as projecting each vector onto Z first, scaling those projections, and then adding them together. And 3, it is positive definite. Think of Euclidean inner product as a normal ruler. It works just like measuring things on flat paper, or in the real world 3D space. Non-Euclidean inner products are those that fill at least one of these three conditions, like in pseudo-geometries, as in general relativity. Since the Euclidean inner product only works naturally in flat spaces, differential geometry extends it to curved spaces by defining it locally, specifically on the tangent space at each point. This is possible because manifolds are locally Euclidean and can be made smooth, which ensures that a well-defined, unique tangent space exists at every point. So no sharp corners or discontinuities here. This way, we can still enjoy the benefits of Euclidean inner product, like measuring lengths, angles, and curvature, while applying it to more general curved spaces.
So there you go, the complete definition of a Riemannian manifold. A space M, which is a C-infinity manifold, in other words, it is Hausdorff and second countable, equipped with a Euclidean inner product GP on each tangent space TPM of the manifold M for all points P in the manifold. In addition, the metric has the nice property of varying smoothly from point to point. These are some quick concrete examples of Riemannian manifolds. Let us know in the comments if you guys would like a video only discussing in detail each of these examples, or maybe just one of them in particular. The simplest and most fundamental Riemannian manifold is the Euclidean space, where the metric is defined this way, so just the dot product. Second, any finite dimensional vector V with a metric G as its inner product. Third, the Euclidean sphere of radius r. The inner product is the one induced from the embedding of the sphere in the space Rn+1. And it is called the canonical inner product of the sphere. Fourth, the hyperboloid model of hyperbolic space. First, we define the ambient space Rn+1 with the appropriate inner product, where the hyperboloid is embedded. Points in Rn+1 are like this, and they're equipped with this inner product. This specific inner product is called a Minkowski metric. And it's not positive definite, because it allows for negative square lengths. In other words, the inner product of two vectors might be negative. We say that this inner product is indefinite, and thus, this space is not a Riemannian manifold, but instead, it is a pseudo-Riemannian manifold, or Lorentzian manifold. In special relativity, for example, if the inner product of a vector with itself is negative in the spacetime diagram, then this is a space-like vector, which corresponds to a path that would require faster than light travel. If you guys want to know more details about this fascinating hyperbolic space, as well as an example of defining a torus as a Riemannian manifold, check out the PDF link in the description. So now we have more than just smooth spaces. We have also a structure and a way to measure it. Riemannian manifolds provide us this structure, and that's why they are so powerful. They are powerful in pure mathematics, but also in general relativity, applied to physics. And again, specifically to space-time, we talk about a pseudo-Riemannian manifold, because the signature is minus plus plus plus, not positive definite as a Riemannian manifold would be. Chapter 9. Gaussian curvature. Some spaces feel flat, just like a table. Other spaces, they curve outwards, like a sphere. Some inwards, like a bowl, or even a saddle. But the point is, how can we capture this idea? How can we be precise with this idea? And that's why we talk about Gaussian curvature. This is specific for surfaces, so 2D spaces. But of course, later on, we'll need to generalize this idea to higher dimensional spaces. Gaussian curvature is a single number that can be positive, negative, or zero. And it will tell you how the surface curves locally. Think of a very interesting space, a huge one, in which some parts of it look like a sphere. Other parts look like a saddle. They curve up in one direction and down in another. Some regions, though, are just perfectly flat. How can we measure these types of warps? How can we quantify this fundamental difference between each region? Gaussian curvature is the answer. And it has deep consequences, not only in pure mathematics, but also in the future of our universe. Gaussian curvature is usually denoted with a capital K. Even though Gaussian curvature is defined only for two-dimensional surfaces, its core idea, so measuring how a space bends, can be generalized to higher dimensions. In cosmology, we apply the same principles to three-dimensional spaces, or 4D spacetime, using tools like sectional curvature and Ricci curvature to describe how the universe bends at each point. Gaussian curvature is defined as the product of two principal curvatures, denoted with the Greek letter kappa. The principal curvatures can be positive, negative, or 0. In order to understand what these principal curvatures are and how to compute them, imagine the following.
This is Luca in a car. Now, he decides to turn to the left. He will naturally feel a force pulling him to the right, though. The acceleration felt by Luca is called centrifugal acceleration in physics. This is actually a fictitious acceleration. The real acceleration here is the one inwards, the one that keeps the car, Luca, and everything inside of it moving along the curved path. This is called centripetal acceleration, and is calculated this way, where v here stands for tangent velocity and r for the radius. But that's the point here. The radius of what? Well, it must refer to a circle, right? But who said that Luca is moving in a circular path? It might very well be a random curved trajectory. And the formula a equals v squared over r still holds. This is a very important concept in differential geometry, and it's called the osculating circle. An osculating circle is the circle that best matches how a curve bends at a point. It shares the same position, the same tangent, and the same curvature. The bigger its radius, the larger the bend. The smaller its radius, the tighter the bend. This connects to the formula v squared over r, which tells you how much acceleration is needed to stay on a curved path. Notice how the acceleration and the radius are inversely proportional to each other. So the bigger the radius, the less acceleration is needed. And vice versa. If you imagine moving along a curve, it's like constantly riding along a chain of osculating circles, and staying on track means always being pulled inward. That pull is what we feel as a force. In physics, this shows up in cool ways, like in general relativity, where gravity isn't a force, but just a consequence of objects following curves in spacetime. Those curves act like osculating hyperspheres, and the tighter the bend, the more things feel pulled inward, just like in regular circular motion.
Going back now to the principal curvatures kappa 1 and kappa 2 of the Gaussian curvature formula, let's connect them to the visual concept of osculating circles. You can cut the surface at any point with vertical planes that contain the normal vector to the surface at that point. Each slice creates a normal curve lying in that plane. Each of these curves has an osculating circle that encodes the local curvature at that point. Out of all possible normal slices, there are two that are very special. The first is the one that produces the normal curve that bends the most, which gives maximum curvature, and is called the principal curvature kappa 1. The second special kind of normal slice is the one that produces the normal curve that bends the least, which gives minimum curvature, and is called the principal curvature kappa 2. These are real numbers. The directions in which they occur are called principal directions, and they can always be proven to be orthogonal. At any point on the surface, in the principal directions, the surface curve through that point, in other words, the intersection of the surface with a plane containing the normal vector and the principal direction, can be locally approximated by an osculating circle. In each principal direction, there is a plane curve lying on the surface. That curve has curvature equal to one of the principal curvatures, kappa 1, 2. And so, it has an osculating circle of radius 1 over the absolute value of kappa 1 or kappa 2. The osculating circles are the best fitting circles to the surface in the directions of principal curvature. Good, but how do we calculate these real numbers kappa 1 and kappa 2? We're going to show you the step-by-step algorithm of how to do it. And after that, you can think of any random surface and try it out on your own. For a more detailed version of this explanation, check out the PDF link in the description. Step 1. Parametrization. Define your surface as a function of two variables. So, a parametrization, in this case u and v. Step 2. Tangent vectors. Compute the tangent vectors at each point by calculating the following partial derivatives. These vectors span the tangent plane at each point. Step 3. Unit normal vector. Calculate the normal vector by taking the cross product of the tangent vectors and then normalize, so that it has magnitude 1. This is called the unit normal to the surface at each point.
Step 4. First fundamental form. Compute the first fundamental form, denoted as a Roman 1. This is a matrix with entries being dot products of the tangent vectors we calculated in the previous step. xu and xv, so the coordinate tangent vectors, are not always orthogonal. So in other words, it is possible that xu dot product with xv is different from 0. But when computing principal curvatures, these tangent vectors form a special orthogonal basis. This means that, in this special case, the tangent vectors will be 0, and therefore their dot product will be 0. Since we're not diving into the theory of differential forms here, we will just think of the first fundamental form as the matrix version of the inner product. It tells us how to compute lengths and angles. It's the metric tensor in the surface's coordinates. Just as, for example, we can represent the metric on flat spacetime this way, and equivalently as a matrix in this way. Step 5. Second fundamental form. Now we compute the second fundamental form, which is denoted as a Roman 2. This is a matrix with entries being dot products of the normal vector and the partial derivatives of the tangent vectors. Again, we will not get into the theory of differential forms here, but the second fundamental form is like second directional derivatives. Think of it as taking a vector, differentiating it twice, and then extracting the component in the direction you're interested in. In this case, this direction is given by the normal vector n. Step 6. Shape operator matrix. This is just the product of the inverse first fundamental form matrix with the second fundamental form matrix. It describes how the normal vector changes as you move along different directions on the surface. Step 7. Eigenvalues. It's the last one, guys, I promise. Compute the eigenvalues of the shape operator matrix. So if the matrix looks like that, we calculate its eigenvalues through the following formula.
If you're curious to see how we got to this expression, check out the PDF link, as always. We finally did it. These eigenvalues are the maximum and minimum principal curvatures kappa 1 and kappa 2. Now, all you have to do is to multiply these two numbers, and then you get the famous Gaussian curvature at each point. Okay, time to see a concrete example, the two torus. Following the algorithm, we find each result for each step. Step 1, parametrization. Step 2, tangent vectors. Step 3, unit normal vectors. Step 4, the first fundamental form. Step 5, the second fundamental form. Step 6, the shape operator. Step 7, the eigenvalues. Once we found the eigenvalues of the shape operator, in other words, the principal curvatures kappa 1 and kappa 2, we can calculate the Gaussian curvature for each point of the two torus. So, for example, for points inside of the donut shape, the Gaussian curvature is negative. For points outside, it is positive. And the Gaussian curvature is 0, so the surface is considered flat only along these lines on top and on the bottom, dividing the outside from the inside regions. The sign of curvature isn't just mathematical curiosity. It has profound implications for the geometry of our universe. And in this context, we move beyond just Gaussian curvature, which apply only to two-dimensional surfaces, and instead we use higher dimensional generalizations. And this way we can describe the curvature of 3D space or even 4D spacetime. These include Ricci curvature, sectional curvature, and scalar curvature. And each of them capture different aspects of how the space bends.
In cosmology, the large-scale shape of space itself could be spherical, so positive curvature, which would be closed, or hyperbolic, negative curvature, which is open, or even flat, zero curvature, and is also open. This is important because it will determine whether the universe will collapse, expand forever, or eventually find equilibrium. Current observations, like those from the cosmic microwave background, show us that the universe is very close to flat. But we still can't say that exactly, because as you can imagine, this is super difficult to measure. In any case, understanding curvature isn't just math for fun. It's about understanding the fate of the universe.
In the end, Gaussian curvature gives a way of understanding how the surface bends locally for each point. It's just one number, and it tells you if the surface is more like a sphere, or more like a saddle, or more like flat locally. And of course, this is the basis to help us understand the structure of the universe, of spacetime. Chapter 10. Ricci curvature tensor. Ricci curvature also captures curvature, just like Gaussian curvature, but it's a sort of generalization, because this time we can work in higher dimensions, so it captures curvature in a more complete way. We'll also talk about positive, negative, and zero curvatures here, but again, in higher dimensions. Take a flat space and place some objects on it. If we were to deform the space, some interesting things would happen. Some areas would feel like they're pulling things inward. Others push them apart. And other areas stay the same. Ricci curvature is the tool that captures this. It tells you how volumes shrink or grow, how paths called geodesics bend together or drift apart. In physics, it connects mass and energy directly to the shape of spacetime. Ricci curvature is more than math. It is how the universe keeps track of what is inside of it. Ricci curvature is very powerful because it applies to any n-dimensional Riemannian manifold, not only to two-dimensional surfaces, like the Gaussian curvature. Ricci curvature is defined as the contraction of the Riemann curvature tensor. We'll see very clearly what it means and what it looks like in a general space. But for now, think of it as a way of measuring how areas, volumes, or hypervolumes, so in higher dimensions, expand or shrink as you move outward from a point.
Ricci curvature at a point in space can behave in three distinct ways, depending on how geodesics respond nearby. If it's positive, geodesics tend to converge. If it's negative, they diverge. If it's zero, they stay parallel, as if space were flat in that direction. In some sense, a geodesics is the locally shortest path between 2 points, like a straight line, but on a curved space instead. It's the path a particle follows if no forces act on it except the shape of the space itself. So, as you can imagine, it's very useful when trying to study the curvature of a space. For example, imagine you're inside a foggy, curved universe, and you release a cloud of particles from a single point, all moving freely in different directions. As time passes, do they spread apart? Do they collapse together? Or do they just stay evenly spaced? This isn't a question of force. There's no force acting on them. It's a question of geometry instead. And that's where the Ricci curvature tensor comes in. It tells you at a specific point how your cloud will behave. Whether it shrinks, stretches, or stays perfectly stable. It fixes the problem by translating the invisible bending of space into something measurable. In other words, the change of volumes. This is a representation of a general Ricci tensor for an n-dimensional space. In 2D, this curvature tensor becomes a 2x2 matrix that describes how space curves at a single point. For example, this matrix tells us that geodesics along the x-axis tend to converge, so positive curvature, while those along the y-axis diverge, so negative curvature. A point in a space that behaves this way is called a saddle point. At this point, the curvature matches this matrix, compressing space in one direction and stretching it in the other. This is just one example, but you can easily imagine how this tensor would change from point to point for different types of curvature. So this is a saddle. Another representation can be a bowl, or an upside-down bowl, or even a point in a flat space.
What about the off-diagonal terms, R01 and R10? They are all zero in these examples. What would it mean if one of them were not zero?
If you're enjoying this video, don't forget to like it and to subscribe to the channel.
In that case, the chosen intrinsic coordinate system is not what we would naturally expect. This is the coordinate system defined on the surface itself, not from an embedding in 3D space. It is not what we would expect because the coordinate axes are not aligned with the directions of curvature. If you imagine releasing particles from a particular point, they would still follow geodesic paths, but these paths would not be aligned with the grid anymore. Algebraically, the off-diagonal terms represent directional coupling. Motion in one intrinsic direction, say x, contributes to the geodesic expansion or contraction in another direction, say y. However, this is not an intrinsic property of the geometry itself, but rather of the coordinate frame that you've chosen. The Ricci tensor is a geometric object, so it exists independently of coordinates, but its matrix representation depends on the basis. If you change to a new intrinsic coordinate system, aligned with the eigenvectors of the Ricci tensor at that point, the matrix becomes diagonal. This process is called diagonalization, and it reveals the principal Ricci curvatures, which are intrinsic and therefore independent of the coordinate choice. Visually, this corresponds to rotating the perspective of the surface. Let's see a concrete example. Say that at a specific point on a curved space, on a curved surface, the Ricci curvature tensor is this. This is a symmetric matrix, because Rij equals Rji. By the way, just a technical detail here. The Ricci tensor is always symmetric. This is a direct consequence of the way in which it is built. In other words, from the Riemann tensor via a contraction. We'll not get into too many details here, but the Riemann tensor satisfies a special symmetry. And this makes the Ricci tensor into a symmetric matrix. Anyway, going back to our example. we can calculate the eigenvalues of this Ricci matrix transformation. Therefore, the diagonalized Ricci tensor is this, which reveals itself as a saddle point.
Notice an interesting fact. Even though the original Ricci curvature tensor looked positive in all directions, it is just the illusion of the quote-unquote bad coordinate choice. Once diagonalized, we see the true story. Curvature pulls space together in one direction and pushes it apart in another. The eigenvectors tell us those directions. They are intrinsic, geometric objects drawn right inside the surface's tangent space.
So Ricci curvature gives us a way of understanding how the space bends, but all of this intrinsically, since it's derived from the metric tensor. And it's not only for a point, it's for a region in space. Sometimes you can look at the matrix representing the Ricci curvature tensor, and it gives you the wrong feeling, because maybe you are using a bad coordinate. But once you diagonalize the matrix, you can see the full story. And that's exactly what we did here. It's a very powerful tool in general relativity, and especially for understanding Einstein's field equations. Chapter 11, Scalar curvature. Scalar curvature is also a single number derived from the Ricci curvature tensor by contracting it with the metric, such that it also gives you the curvature of the space in that point. It's like an average curvature. We can also use it for higher dimensions. We're not restricted to 2 dimensions like was the case with Gaussian curvature. So we talk about areas, volumes, and hypervolumes here. And by the way, this also appears in Einstein's field equations, so pay attention. Imagine you are walking on a surface. If the surface is flat, you can draw a tiny circle by rushing on straight lines in many directions, then laying out dots that are all the same distance from the initial central position. Now you measure its area. The result is exactly what you would expect from Euclidean geometry. In differential geometry, there are in general 3 kinds of curvature: positive, negative, and zero. In a positively curved space, if you draw that circle around you, the area will be less than expected. In a negatively curved space, the area will be larger than expected. Now, the question is, how can we capture this circle distortion as a number that captures how curved the space is? And all of this right at the point we're standing. That's where scalar curvature comes in. It's denoted with the capital letter R, and it is a way of capturing how much a space around a point is curving. You can also think of it as the average amount by which circles drawn around that point shrink or expand compared to its flat version. Of course, this is the 2-dimensional case, in which we talk about the variation of area of curved circles with respect to flat circles. In 3 or higher dimensions, we talk about volumes or hypervolumes of balls, with small radius epsilon greater than 0 around the point we're interested in. The scalar curvature tracks how much this volume differs from what it would be in a flat space for each point. The result is a single number at each point. If it is positive, the ball shrinks. If it is negative, the ball expands.
Now it's time to be a little bit more rigorous. We'll see an algorithm to calculate the scalar curvature R of a general n-dimensional Riemannian manifold. We also attached a very clear written explanation in PDF, just as we do with all of our videos. So check out the PDF link in the description of this video as well. Don't worry about the technical terms you don't understand yet. We'll get to each one of them. As one of the great mathematicians, John von Neumann, said, in mathematics, you don't understand things, you just get used to them. Anyway, let's get into it. This is the step-by-step algorithm. First, choose a Riemannian metric for the manifold. Second, calculate the inverse metric. Third, compute the Christoffel symbols. Fourth, calculate the Riemannian curvature tensor. Fifth, compute the Ricci curvature tensor. And sixth, calculate the scalar curvature. Okay, as you can tell, that's a long process. The main issue here is that there is what we call the Matryoshka effect. Each step consists in calculating a quantity that is nested inside of the other, just like Russian dolls. This makes the algorithm sort of clumsy, and that's one of the reasons symmetries play an important role. They help us to simplify and shorten a lot of calculations. As a very simple illustration of the power of symmetries, imagine a quadrilateral, and I tell you that one of its sides measures 1 centimeter. Just by imagining and trying to sketch such a figure, you could attempt to approximate the lengths of the other sides, and maybe estimate the angles, but it's still really difficult and imprecise. However, if all of a sudden you're introduced just one extra piece of information, in other words, a symmetry, for example that this quadrilateral is a square, then you can basically calculate everything you want about it. In a similar way, when working with these tensors, so Riemannian metric, inverse metric, Riemann tensor, Ricci tensor, and so on, we will find many dependencies between its components. These dependencies are called symmetries, and they simplify our lives a lot. If you're enjoying this video, don't forget to like it and to subscribe to the channel.
One illustration of it is the fact that the Ricci tensor is symmetric, so its matrix form can be diagonalized. Let's revisit the first step of the algorithm, Riemannian metric. Imagine a smooth manifold M in n dimensions. A Riemannian metric G is a map that assigns at each point P in the manifold M a way of measuring lengths and angles between vectors. As you can see, there are many possible formulas or maps that fit this definition of a Riemannian metric. It is usually not unique. Anyway, you can think of it this way. You feed in two tangent vectors at a point P, and the metric spits out a real number, which is the result of their dot product, since, by definition, the tangent space at each point is a Euclidean space, so it's flat. If the output is 0, it means that the vectors are orthogonal to one another. If the result is not 0, then it measures how much they align. If the two vectors are the same, the output is the square length of the vectors. This metric can be expressed as a matrix, so Gij with its indices running from 1 to n. The diagonal entries are the squared lengths of the basis vectors. This way, the matrix becomes the following. These are the diagonal terms. If the space is Euclidean, all the diagonal terms are 1, because the basis vectors are versors. In other words, their length is 1. But in curved spaces, they can vary with position and be different. The off-diagonal entries are inner products between different basis vectors. These dots here represent the inner product under the Riemannian metric. So they measure how non-orthogonal the coordinate directions are at a point. And now the matrix becomes this. If one of the entries is 0, then the vectors are orthogonal. If it is not 0, then they are tilted with respect to each other. Okay, once you define your Riemannian metric, you can move on to step 2. 2. Inverse matrix. The inverse matrix, by definition, is a matrix that, when multiplied by its original version, results in the identity matrix. So the diagonal terms are 1, and the off-diagonal entries are 0. There are many techniques in linear algebra to calculate the inverse matrix, but we'll not see them here. 3. Christoffel symbols. These are mathematical objects that track how the coordinate directions tilt across the manifold. They encode how to differentiate vectors smoothly in curved spaces. Christoffel symbols are calculated in the following way. So 1/2 of the inverse matrix times the sum and subtraction of the partial derivatives of the metric. This looks scary, I know. As you can see, the Matryoshka effect is escalating really quickly. Notice how this object has three indices, I, j, and k. This means that we can imagine it as a sort of three-dimensional matrix. Each entry corresponds to a component of the Christoffel symbols, which are all real numbers. Four, Riemann curvature tensor. Think of the Riemann curvature tensor as describing how the Christoffel symbols vary around loops. It captures the cumulative tilting effect when transporting vectors around closed paths. It is computed through the following formula. So the partial derivatives of the Christoffel symbols plus these multiplications of Christoffel symbols. The Christoffel symbols describe how vectors change infinitesimally in a single direction. The Riemannian tensor is built from derivatives of the Christoffel symbols and their combinations. It detects how geometry changes across two directions, so over a loop.
5. Ricci curvature tensor. The Ricci tensor measures how volumes deform when you move through space. It tells you how geodesics converge or diverge depending on the direction you move. We start from the Riemann tensor, which has 4 indices. It can be thought of as a 4-dimensional hypercube. If we're describing the 4-dimensional spacetime, for example, with entries that are just real numbers. Of course, the more general case would be the one in which we have an n-dimensional cube. In order to compute the Ricci tensor, we slice through this cuboid, and then we add up a row of values in a particular cross-section. The result is a sort of summary of the curvature in each direction. This process is called a contraction. It is actually just a fancy word for summing along a repeated index, which shrinks the dimensionality of the object, like from 4 to 2 dimensions. It is similar to taking the trace of a matrix, but extended to higher dimensions. And finally, 6. Scalar curvature. As we've seen before, the scalar curvature is a single number at each point that summarizes how the space is curved, on average, in all directions. R is a real valued function, so a zero-ring tensor, which is obtained by collapsing the Ricci tensor into a single number. This is done by summing over both indices of the Ricci matrix using the inverse metric, so a double contraction. In conclusion, the Ricci matrix tells us how much the space curves and distorts volumes when moving in a specific direction. The inverse matrix, Gij, tells us how to average these directions and provides a geometric tool for doing so. The product between the inverse metric and the Ricci tensor gives a sort of weighted average of curvature in all directions. And this is the scalar curvature R. This quantity, so the scalar curvature R, answers the following question. At a specific point on the manifold, is the curvature, on average, positive, negative, or zero around its neighborhood?
In conclusion, the scalar curvature gives us how the space bends at a specific point. It's a single real number, and it's a very good way of summarizing curvature locally. Chapter 12, Conformal Geometry. When we talk about curved spaces, we have a picture in our brains of like a space bending in another higher dimensional space, like a distorted version of it. But how can we bring this concept in a more mathematical way? Using mathematical terms. We need to be precise here. In other words, how can we mathematically measure spacetime and be sure that it is curved? Well, it depends on your definition of curvature. From the purely differential geometry point of view, we need to talk about intrinsic properties. Theoretically, we could have a flat sheet, using our definition of flat, our intuitive definition, that perfectly mimics the curvature of a sphere, for example. And only from measurements inside of the space, we can't really tell if we live in a curved space or in a flat space. And that's exactly something that happens to us when we're studying general relativity and cosmology, and we're trying to understand the curvature of the universe in a large scale. So there will be many implications here. I just want you guys to be ready. So open your minds about the definition of curvature and always think in intrinsic terms. Space-time is not necessarily curved around massive objects. There's no way to look only at the mathematics of general relativity and say for sure that matter produces curvature of the four-dimensional manifold model of space-time. At least not using the definition of curvature adopted by most people, including some mathematicians and physicists themselves. The formalism used to describe space-time in general relativity is given mostly by differential geometry. But the interpretations of the purely mathematical results require more than math itself. They require physics, or even philosophy, if you will. Let's see an illustration of what I mean. Suppose you want to measure the area of a circle of radius r. If you know the value of r, let's say 2, then you can calculate the area with the following formula, pi r squared, and then we find the area to be 4 pi. Now, let's do the opposite. You are given the value a equal to 4 pi, and you are asked to use the same formula to calculate the variable r. You can calculate its inverse, so r is plus or minus 2. At this point, strictly speaking, from the purely mathematical point of view, you find two possible values for the quantity r, so plus or minus 2. Especially in pure algebra, both results must be considered valid. Of course, if you interpret the variable r as the physical distance from the center to any point at a circle, then it is meaningless to consider the negative value. And that's why at this point of our calculations we discard it and pick r equals plus 2 as the only possible value of the radius. This process of discarding a purely mathematical result in favor of a choice that provides physical meaning is the bridge that we cross from pure mathematical end to physical end. There's nothing wrong with it, but it does require some element of interpretation, and interpretations might be subjective sometimes. Indeed, there are some specialized areas in mathematics, like sign-to-distance fields in computer graphics or oriented geometry, where negative radii is informally assigned meaning. So the point here is just to be careful when trying to interpret results in pure mathematics.
Let's see how this illustration connects with our context here. So calculating purely mathematical results in differential geometry and then interpreting them physically in the case of spacetime and general relativity as a whole. Imagine a sphere of radius capital R. This is obviously a curved space, right? Well, we know that because its Gaussian curvature is not zero everywhere. In fact, it's not zero anywhere. Gaussian curvature tells us if the space has positive, negative, or zero curvature. For the sphere of radius r, the Gaussian curvature formula is precisely this: everywhere for all points. If the radius tends to infinity, the curvature tends to 0. In other words, the sphere becomes flatter and flatter, approaching the geometry of an infinite plane, which has 0 curvature. On the other hand, if we imagine that r tends to 0, then the sphere shrinks to a single point, so singularity, and its Gaussian curvature at each point diverges to infinity. This means that the notion of smooth geometry breaks down. Okay, now that we have some intuition on Gaussian curvature, let's construct a weird infinite plane. The weird thing about it is that even though it's flat, the metric used to measure local distances, so the sort of ruler defined in the space, depends on the position of each point with respect to the origin.
Anyway, let's see an example of a two-dimensional object placed near the center of this peculiar plane. After placing it there, the object undergoes almost no deformation, but as it moves away, it experiences a contraction. Its radial length progressively decreases, with the effective size tending to 0 at infinity. In this sort of elastic plane, the underlying topology remains the same as that of the flat real plane R2. However, the local measurements of lengths, areas, and geodesics behave exactly as if the space were intrinsically curved like a sphere of finite radius capital R. In other words, in a certain sense, this plane perfectly mimics the sphere in such a way that, strictly from the point of view of differential geometry, not taking into consideration their overall topological features, this plane is indistinguishable from the sphere. it is impossible to perform any calculation or measurement of intrinsic quantities related to curvature that would allow beings in these spaces to find out whether they live in a sphere or in a plane with a position-dependent metric. Now, before you guys start cursing me in the comment section, let me tell you that this originally was not my idea. I got that from Feynman in his book Lectures on Physics, Volume 2, last chapter, number 42, titled Curved Space. Mathematically, this effect is achieved by equipping the plane with what is called a position-dependent conformal factor, which is applied to the flat metric, where little r here is the radial distance from the origin, and capital R is the radius of the sphere that we want to mimic. Okay, I don't know about you, but I find this fact super cool. Before continuing though, let's take a step back and see the three different metrics involved here, as well as their interpretations. The first one is the standard metric of flat two-dimensional Euclidean plane R2 with xy coordinates. Here, distance between points are given by the Pythagorean theorem. Geodesics are straight lines, and the Gaussian curvature is zero everywhere. Pretty standard. The same metric can be expressed in polar coordinates. Second, the standard metric of the sphere with radius capital R. Geodesics are not straight lines anymore, but only from our privileged point of view, observing the scene in 3 dimensions. Gaussian curvature is constant and positive everywhere, 1 over r squared. And third, the position-dependent stretched metric on the plane. In other words, the conformally flat metric. This is just like the flat metric that we've seen before, but with each point multiplied by a conformal factor, so a number that depends on the radial distance from the origin. What about its Gaussian curvature? Is it still zero? In general, for a conformal metric like this one, the Gaussian curvature k is calculated with the following formula, where delta here is the flat Laplacian operator in polar coordinates. Now, plugging in our conformal factor in this equation, we get the following, which is identical to the Gaussian curvature in the sphere. If you want to see the detailed calculation, check out the PDF link in the description, which comes with a summary of the video and other additional things. The math is not complicated, so we think that most of you guys will be able to follow along.
If you're enjoying this video, don't forget to like it and to subscribe to the channel. Beyond that, we can compare geodesic paths on the sphere with the ones on the conformal plane. In order to find geodesics, we need to solve second-order, nonlinear, autonomous ordinary differential equations that are defined on our smooth manifolds. In our case, the sphere and this conformal plane. These are the Christoffel symbols, or the coordinate representation of an affine connection. They tell us how to slide a vector forward while staying parallel to itself on a curved surface. T here is a so-called affine parameter. Think of it as the natural clock along a geodesic. In classical mechanics, it's often interpreted as Newtonian time. In general relativity, for example, it becomes proper time, for time-like paths. This interpretation is not always valid, but just to get a feel for what we're measuring here, this intuitive frame will be enough. These are the coordinate bases, which for the sphere will be this. And for the conformal plane, this. Pay attention. Both of them have variables denoted as theta, but they track different angles in each space. This is actually a coupled system of 2 equations for the function x mu. From the theory of ordinary differential equations, each geodesic equation admits a unique solution for any given initial point at t equals 0 and initial derivative, so velocity. The result is just the famous Cauchy problem, which means that geodesic paths are uniquely determined by their initial position and direction.
Now, let's use the standard metric defined on the sphere in polar coordinates in order to find the geodesic equations of the space. To start, we notice that we need to calculate the Christoffel symbols first. But how do we do it? Well, following the order given by the Matryoshka effect, we see that we need to explicitly write down the metric g mu nu and its inverse. Now we can plug them in the Christoffel symbols formula, taking into consideration that we're working in 2 dimensions, and the indices can have only the following 2 values, theta or phi. We won't show the details here since the calculations are really long. But as always, we did the heavy lifting for you by adding every little step of this process in the PDF link in the description. Check it out. In any case, these are the results. Finally, plugging them in the geodesic formula, we get these 2 geodesic equations. Solving them simultaneously gives us all possible geodesic paths on the sphere. We did the same process with the conformal plane and found these geodesic equations. Okay, to say the least, these 2 systems of nonlinear ODEs are very hard to solve in general. Solutions of the sphere are just great circles. This is not a great circle, for example. But this one is. Great circles have their radius identical to the sphere's radius. Solutions of the geodesics on the conformal plane, on the other hand, are a bit more difficult to find, even though the sphere and the conformal plane are equivalent as far as curvature is concerned, except for a point at infinity in the conformal plane, which corresponds to the south pole in the sphere. These are some solutions on the conformal plane. First, uniform circular motion, so either the trivial solution with r equals 0, or little r equal to capital R, the radius of the sphere. And the second one is the radial motion with no angular change. Again, check out the PDF to see how we found these solutions.
In conclusion, in differential geometry and general relativity, we say that spacetime is curved. But what we actually mean by curvature is that the spacetime manifold has non-zero Riemann curvature. And this implies that vector fields fail to commute under parallel transport, and that geodesics are non-trivial. But there's a big difference between saying that a space has curvature and saying that it's literally bent in some higher dimensional direction. And honestly, that's the non-rigorous picture people have in mind when they talk about curvature. This literal bending is just a visual metaphor. But it's not mathematically accurate from the strict point of view of differential geometry. So, using the definition of curvature in differential geometry, spacetime is definitely curved. But when using the loose definition that most people have, which assumes curvature to be bending into an extra dimension, then spacetime cannot be considered necessarily curved in the presence of matter. Now, it's important to notice that not all geometries are conformally flat. A manifold is conformally flat if there exists a coordinate system in which the metric is a scalar multiple of the flat metric. In 2 dimensions, every surface is locally conformally flat because of something called the uniformization theorem. But in higher dimensions, the situation is way more complex.
And this is exactly what gave birth to many alternative theories of gravity. For example, conformal gravity says that the spacetime metric is defined only up to a scaling. In other words, the true geometry is conformally invariant. Whale geometry is an example of such theories that generalizes general relativity. Another one is the twistor theory, developed by Penrose, and there are others. Of course, if conformal gravity or alternative theories will replace or generalize general relativity, then we need experiments to validate them. This is out of the question. One would need to show that a non-trivial Riemannian tensor does not imply intrinsic curvature in the physical sense. Until then, conformal models remain very interesting from the mathematical point of view, but will they pass the full empirical tests of reality? Let us know your thoughts. So conformal geometry teaches us that curvature isn't just about shape. It's about what you measure and how you measure it. A flat space can mimic a curved space, depending on the metric you give to it. And this little shift of understanding will really help you to get intuition about general relativity and differential geometry. So remember, when we're measuring curvature, you need to look for the metric tensor. This is the intrinsic property, as well as all the other quantities that come as a consequence of the metric tensor, that will give you the true story about the curvature of the space you are dealing with. Chapter 13, Metric Tensor. I like to think of the metric tensor as a structure that lives beneath our space, or the space we're studying, like spacetime. It is the tool that allows you to measure distances and angles. And as a consequence, it will be crucial for you to measure whether the space you are dealing with is curved and how curved it is. It isn't like a ruler that you can hold in your hands, but it's more like a manual that you can read and understand how to proceed in order to measure what you want. The metric tensor is really, really important because that's what we mean when we talk about solutions to Einstein field equations. I would say that understanding the metric of a specific space is probably the most important thing you need to learn in this context. We're surrounded every day by curved objects: roads, bridges, hills, and apples. But did you know that there is a deeper structure to reality most people never think about? This structure dictates how objects move from the path of a falling iPhone to the macro scale of the universe. Beneath every curve in a space, there is a hidden formula ruling it all. It is called a metric. And understanding it is like gaining access to the operating system of the universe. Imagine you were a kid playing basketball in your backyard. The ball bounces out of bounds and gets stuck in a tree. Classic. So you grab a ladder to get it down. Of course, you would need to adjust its height so that it is greater than the distance between the ground and where the ball is located on the tree. This means that you would need to create a right triangle, such that the angle formed between the ground and the ladder is less than but close to 90 degrees. Let's say 85 degrees. Otherwise, the friction force would not be strong enough to hold you still. Anyway, that's not the point here. The point is that all of these things, so lengths, angles, can be easily measured once you assume that we live in a Euclidean flat three-dimensional space, which is a pretty good approximation. What we often fail to notice, though, is that when performing these calculations, we're also assuming a specific ruler or a specific protractor as the only available option. This is the standard Euclidean metric. However, there are others. For example, the matrix 2, 0, 0, 0, 1, 0, 0, 0, 1, which is a metric in flat space, but not an Euclidean one, because it is not proportional to the identity matrix. This metric stretches distances in the x direction compared to the y direction. It basically says that one unit step in x is twice as long as it would be in the Euclidean metric, but one unit step in y is unchanged. It is definitely a bad physical model for our adjustable ladder and tree illustration, but mathematically it is consistent. So it really depends on the context. The bottom line is that the metric is just a matter of convenience, a choice.
Now imagine you're not in your backyard anymore. Instead, picture yourself in a landscape with rolling hills. You try to draw a large triangle on the ground, but something seems off. You sum up the angles that you measured, but they just don't add up to 180 degrees anymore. In some regions, the result is greater than 180, and in others, it's less than 180. Well, the issue is obvious, isn't it? The space you're dealing with is not flat anymore. It's curved. And now your Euclidean rulers don't work anymore. Geometry depends on the metric that defines how things are measured, locally, at every point. Here, you can still draw triangles, but not the Euclidean ones. The rules have changed, and the metric is the new rulebook now. At each point in this field, there's a sort of instruction manual, like a tiny blueprint, that tells us how lengths and angles should behave in the immediate neighborhood. This instruction manual is the metric. So instead of thinking about the metric as a straight ruler, imagine it's more like a guide or manual given to every point of space. It tells you, if you want to move just 1 unit north and 1 unit east, how much ground will you really cover? If you rotate something, what angle have you swept based on how this region bends? And if you try to go straight, what does straight even mean here? If you're enjoying this video, don't forget to like it and to subscribe to the channel. The neighborhood of each point will obey its own set of rules locally, dictated by its own metric. And the way these instructions connect across the surface defines the full geometry globally. That's what makes the metric so powerful. It's locally defined, but its compound influence is global throughout the entire space. Great. Now that you have the intuitive picture of what a metric is, let's dive deeper with a concrete example. This is a two-dimensional space. I know it looks flat, but it's not, because we will define a non-trivial metric in it. The metric will be defined by this matrix. This metric is called a Poincare half-plane metric, and can also be expressed this way. This will represent only the upper half. This is a space with constant negative curvature, so its Gaussian curvature is -1. And geodesics are either vertical lines or semicircles orthogonal to the x-axis, so they diverge. This is a hyperbolic space, by the way. How can we use this metric to measure distances? Let's say we want to measure the distance from the initial point 0, 1 and the final point 1, 3. To compute distances, we need two things. First, the geodesic curve gamma that connects the initial point to the final one, and two, to integrate the line element ds along this curve. Let's rewrite it using our own metric in this example. Well, let's calculate it.
What we want to find is the curve gamma, or y of x, between 2 points by minimizing the length functional. This is a classic problem in calculus of variations. The integrand is also called the Lagrangian, and it can be represented this way. All we have to do is apply the Euler-Lagrange equation. But since f here doesn't depend explicitly on x, we reduce the Euler-Lagrange equation to the Beltrami identity. I know it doesn't seem so, but this is a great simplification of the problem. For more details, as with every video in the channel, check out the PDF link in the description. Then we plug this equation in the second. And that's what we get. We'll see shortly what the geometrical interpretation of this constant is, but for now, try to guess it on your own. Anyway, we can isolate y prime instead, and doing so, we can clearly see that this is a first-order differential equation for y of x. Well, we can solve it. And after doing so, that's what we get. Therefore, geodesics in the Poincare half-plane are exactly Euclidean semicircles centered at the point x0, 0, and vertical lines are special cases in which the center is at infinity, so r tends to 0, or what is equivalent, c tends to infinity. Finally, we're ready to calculate the distance between the initial point 0, 1 and the final point 1, 3. We solved it analytically in the PDF link below. It was not easy, I gotta say, but the math we used was simply beautiful. Therefore, the shortest path between points 0, 1 and 1, 3 in this space is 1.2158, which is less than the Euclidean distance using the Pythagorean theorem. Actually, it is 45.64% less. Okay, it's time to review some of the things we talked about here, but rigorously this time. Let M be a smooth manifold. A metric on M is a function that assigns to each point P in M a map, such that GP is bilinear. So, for all A and B in the real line, and for all U1, U2, and V vectors in the tangent space at the point P, this relation is valid. Of course, this is also valid for the second argument. Second, GP is symmetric, which can be translated into this equation. Third, GP is non-degenerate. So if GP of UV is 0 for all vectors v in the tangent space, then the vector u must be the null vector. And fourth, the mapping from point P to the result of the metric is smooth for all smooth vector fields u and v on M. This means that the mapping G is infinitely differentiable, so it is C infinity. To finish the video, we'll propose an exercise. And as usual, we added its detailed solution in the PDF link in the description. Check it out. Let H be the Poincare half-plane. Then it is equipped with this metric, just as we've seen before. Your task is to compute the hyperbolic distance from points 0, 1 and 0, 3 using this metric. And I gotta say that this time, the path is gonna be a vertical straight line from the initial to the final point. In general relativity, we denote the metric with the letter G. And this isn't because it stands for gravity per se, but because the metric is the gravitational field of Einstein's theory. In Newtonian physics, gravity is a force. But in general relativity, gravity is the geometry given by the metric. And of course, that comes as a consequence of matter and energy. Chapter 14. Tensor calculus. Tensors are the language of modern geometry. Scalars and vectors are good and enough when we're talking about simple cases. But for curved and abstract spaces, like the ones we deal with in general relativity, we need something stronger. Tensors let us describe quantities that live in every point of the space, and they transform properly when we change perspective. Their ranks tells us how many inputs they eat and what kind of outputs they produce, like scalars, vectors, or even other tensors. An important distinction is that there are some tensors that are covariant and others contravariant, and we'll see the difference between them. But in this chapter, I want you to be able to appreciate the fact that tensors are all about transformations. No matter how you rotate, stretch, or skew your coordinate system, physical quantities like velocities and forces must remain unchanged. Tensors allow us to raise or lower indices and switch between bases, and all of this preserving the most fundamental things about the manifold. Imagine a scalar as just one number floating inside of a box. This value can change as you want, and the range of all possibilities is most often tracked by the real line. What about a vector? One of its representation, but not the only one, is an array of scalars, each inside of their own box, lined up in a specific order. Each box can be tracked by its own version of the real line, for example. Each number tells you how far to go in a certain direction. In 3 dimensions, for example, you'd find 3 numbers, and their respective real lines are usually called x, y, z. This is a vector, in this case, a one-dimensional array of numbers, and the number of entries depends on the dimension of the space you're in. Using the same sort of analogy, what is a matrix? It can be represented as a table. Each column corresponds to an input direction, and each row to an output direction. So it maps vectors in an n-dimensional space, Rn, to vectors in an m-dimensional space, Rm. And that's a matrix, an array of arrays. What happens if we continue to extend this idea to arrays of arrays of arrays of arrays and so on? Notice that the layers or the collections of arrays has nothing to do with the dimension of the space we're working in. For example, think about an array of arrays, so a matrix M, that maps 3 vectors to 4 vectors. This matrix maps a 3-dimensional space into a 4-dimensional space. However, it is an array of arrays, In other words, just two layers or collections of arrays involved here. It has nothing to do with the dimensions of the underlying spaces. This number of layers or collections of arrays is called the rank or order of a tensor. And by the way, all the mathematical objects that we've seen so far in this video are tensors.
A vector is a tensor of rank 1 because there's only one array involved here. But a matrix is an array of arrays, so it's a tensor of rank 2. A scalar is a weird array because it contains only one entry, so it's not really an array. It has 0 layers or collections of arrays. That's why we say that it's a tensor of rank 0. There are also tensors with higher ranks, like a tensor with rank 3, which can be represented with a 3D cube of scalars. But again, it's just a representation. The rank of a tensor has nothing to do with the dimension of the space it lives in. It's too clumsy to draw here, but each of these entry boxes would have their own real lines sticking out of them as their range of possible values. Continuing with the same logic, a tensor of rank 4 can be seen as a 4-dimensional cuboid. It's impossible to draw, but you get the idea. Actually, not all tensors of rank 3 eat 3 distinct vectors, as shown here, and spits out a scalar. There are some tensors of rank 3 that eat vectors and spit out vectors too, or that eat and spit out covectors. These distinctions come from the concepts of covariant and contravariant basis. But before that, what's a covector anyway? Think of a vector as an arrow on the real plane with its standard coordinate bases I and j, for example. The covectors are right there, staring at you, but you can't see them because the basis is orthogonal. But what happens if we tilt the basis axes this way? Can we still describe the vector x as a linear combination of the elements of the basis? The answer is yes, but we have two options now, so a duality. Either we can decompose the vector x using dashed lines that are parallel to the basis axes, or using dashed lines that are perpendicular to the basis axes instead. Both representations are valid, but as you can see, its components are different. In the first representation, we choose to depict the components, which are just real numbers by the way, not vectors, with superscripts. In the second type of decomposition, we use subscripts instead. Actually, the second representation, when written this way, is wrong, because the unit vectors I and j are usually only used for the parallel projections. The question is there an alternative basis such that a linear combination of the elements of this new basis with perpendicular projections allows us to express the vector x? The answer is yes, and it's called the dual basis. Our original basis, defined by parallel projections, is usually denoted with E1 and E2, which are subscripts, such that the little hats indicate that these are unit vectors, so their lengths are 1, and it's called the contravariant basis. The vector components are x1 and x2, superscripts. I know it's kind of confusing, because the basis vectors E1 and E2 are written with indices down, but the components of the vector are denoted with the indices up. Don't worry about that yet. We'll talk a little bit about index notation and Einstein summation a little bit later in this video. For now, don't pay much attention to whether the indices are up or down. Just focus on distinguishing in your mind when we're dealing with a contravariant basis, opposed to the other type of basis, called covariant. Also, it's important to remember that these components, x1 and x2, are nothing but real numbers.
Now, its dual basis, defined by perpendicular projections on the original basis axis, can also represent the vector x by parallel projections on its own basis axis. These are denoted as E1 and E2 superscripts. This is called the covariant basis, and the vector components are real numbers denoted as x1 and x2 with subscripts. Any two bases, E1 and E2, subscripts, and E1 and E2 with superscripts, are dual with respect to each other. And this is so if they satisfy these conditions. Ej dot product with Ei results in the Kronecker delta, or the identity matrix. This means, for example, in 3 dimensions, that E1 subscript is orthogonal to E2 superscript, and also to E3 superscript, but not to its counterpart E1 superscript, in other words, its own dual. The same is valid for E2 subscript. It is orthogonal to E1 superscript and to E3 superscript, but not to its own dual E2 superscript. And the same is also true for E3 subscript. If you are enjoying this video, please do not forget to like it and to subscribe to the channel. These elements, E1, E2, E3 superscripts, in the dual basis are called covectors. When the basis is orthogonal, the dual basis coincides with the original basis. So the basis EJ superscript can also produce or describe other covectors as well. If EI subscript is a basis for the vector space V, then EJ superscript is its dual basis for its dual space V star. Any covector omega in V star can be written as omega j, EJ, subscript and superscript, respectively, or simply as the sum omega 1, E1 plus omega 2, E2, and so on. Using a similar logic, we can talk about co-matrices, or actually covariant matrices. And this, of course, happening in a non-orthogonal coordinate system. And we can also extend it to tensors of higher ranks. We won't discuss them in detail here, but I'll tell you that the core of tensor calculus lies exactly in understanding how geometric and physical quantities transform when the basis is non-orthogonal, which is something that happens very often, especially when studying abstract curved spaces. Tensors provide the language to translate from contravariant to covariant basis, and vice versa. So basically from the original to the dual basis, back and forth. And this is done by raising and lowering indices. A contravariant vector is written with an upper index. It transforms oppositely to the basis. This means that if you imagine a vector v as a physical arrow in space and change the coordinate basis, say you rotate the basis, axis, or stretch them, then the components vi superscript in the vector v will change, but the physical arrow stays the same. It's invariant in space. As you can see, contravariant vectors, like this one that we've just seen, are great to describe physical quantities, such as velocities, displacements, forces, and so on. Because these things are not supposed to change in general just because you decided to use different measuring sticks, or even the same ones as before, but with different angles. That's why you'll often hear physicists saying things like, contravariant vectors are more natural. They correspond to how geometric quantities exist independently of the coordinates. So for example, say that the basis axes are scaled by a factor of 2. Then the components v1 and v2 will be scaled inversely. In other words, by a factor of a half. So they transform opposite to the basis. This keeps the contravariant vector invariant. Great. But what about the basis covectors? In other words, the covariant basis vectors. Imagine you have a vector space with non-orthogonal basis EI subscript. Its dual basis has a basis EJ superscript. Since these bases are dual with respect to one another, by definition we have that their dot product results in the identity matrix, and that each vector is orthogonal to all the other covectors except for its own dual. Now suppose that we change the contravariant basis with a rotation. The covectors in the dual basis can't just be unchanged, otherwise the condition for duality would not be satisfied. The new covariant basis still has to be orthogonal to the new contravariant basis, except for their own individual counterparts, of course. And that's why we say that the dual, so covariant basis, transforms along, so together, with the original, so contravariant basis, in order to maintain consistency. That's the goal of tensor calculus, to express invariant truths, even if the coordinate basis and the coordinate systems change. Therefore, Tijk, written this way, is a rank 3 tensor with one contravariant index and two covariant indices. The only problem is that now we have a tensor that is not purely contravariant nor purely covariant, but rather a mix of both. As a consequence, its explicit version in terms of basis vectors and covectors looks like this. Here, this symbol means tensor product, and it allows us to combine covariant with contravariant bases. At this point, maybe some of you are asking yourselves, what about a super-duper general tensor? What does that look like? This that you are looking at is a rank PQ tensor, where P and Q are natural numbers. Remember, you can think of the components of this tensor organized in a sort of P plus Q dimensional hypercube. Notice, for example, that in the case of a rank 1,1 tensor, we write the first I as a superscript for its components, and for the corresponding basis vectors as a subscript. The same up and down convention is used for J. This is not a coincidence. It is the famous Einstein summation convention. Every time you see the same index appearing twice, one of them up and the other down, it means that you should sum them. And the tensor is said to be contracted in this index. Yes, as you can see, writing this tensor explicitly results in a huge expression, and that's why some people say that Einstein's greatest contribution to pure mathematics was his summation convention. Einstein went even further by informally referring to tensors simply using their components, Tij. This perspective became so intuitive and practical, especially in physics, that it influenced even pure mathematicians working with tensors. Unfortunately, we won't have time to see all the important things about tensors. But this is a list of the main concepts that anyone who's serious about learning tensor calculus should know.
Okay, to conclude the video, we'll see some very useful examples of tensors that you've probably encountered in many different contexts. And if you've never seen them before, you might want to pay close attention because they show up really often in pure and applied areas of math. The metric tensor Gij. The type is rank 02. It measures distances and angles on a manifold, like Riemannian metric tensors or pseudo-Riemannian ones, just like in general relativity. The second, the Riemann curvature tensor, Rijkl. The type is rank 13. This tensor encodes intrinsic curvature of a manifold at each point. 3. The torsion tensor, Tijk. The type is rank 12. This tensor measures how much twist happens when you try to move vectors around in space. In other words, it measures if moving from A to B results in a different direction compared to moving from B to A. In this case, the torsion tensor is not trivial. The Ricci tensor, Rij. The type is rank 02. It's the contraction of the Riemann tensor on the first and third indices. As a consequence, it's purely covariant, and it encodes how volumes distort under curvature.
So we saw that tensors are multidimensional arrays that allow us to describe physics and geometry. They show how quantities behave across space, no matter how we choose to observe or measure them. Chapter 15, Intrinsic Curvature. When people hear that the universe is expanding, a natural question that follows is this: but what is it expanding into? I mean, it's a fair question, but it shows that this person doesn't have mathematical intuition. At least not the correct one in the context of differential geometry. In this chapter, we'll see that if something is expanding, it doesn't mean that this thing is expanding inside of something else. It doesn't mean that there is an outside world. Geometry can stretch internally, changing distances, areas, volumes, and all of this without an outside world. So basically, we are talking about intrinsic geometry again. That's a very important concept. So let's see how to answer this interesting question in this context of differential geometry. What is the universe expanding into? The short answer is nobody knows. But when people say that, what they actually mean, what they actually want to know is, how come physicists say that the universe is expanding if they don't even know what it is expanding into? Even though this is a better way of formulating the question, it exposes a clearly flawed assumption that if something expands, it must expand inside of something else. But here's the thing. Expansion and being inside of something are two completely different concepts. They are independent from one another. Unfortunately, physics alone, as well as intuition, is incapable of explaining this distinction, and that's where the confusion lies. In pure mathematics, if you take a space of dimension n, you can choose to embed it in a higher dimensional space, say n plus 1 dimensions or more, or even in a space with the same dimension n. This larger space is called the ambient space. So, for example, you could embed a point, which is 0-dimensional, into a line, which is 1-dimensional. You could embed it into a plane, 2D, or into a cubic region, 3D, or into the surface of a sphere, 2D, or even into another point, 0D, and so on. What about a line segment? Well, you could embed it into a line, into a cube, or even into a curved sheet. In this last case, the line segment lost one of its properties, since it's not straight anymore, right? Not necessarily.
First of all, what is an embedding? An embedding is a map that associates each point of a source space to a unique point in a tangent space, such that, first of all, the points stay distinct, so no two different points in the source space get mapped to the same place. And second, the shape and structure of the source space are preserved. So the topology does not change, like preserving continuity, genus, and the openness of subsets. If you want a rigorous explanation of all the concepts we talked about here, check out the PDF link in the description. Just like with all of our videos, there you'll find a written summary of the video with a bunch of extra details for you to learn better, faster, and deeper. For example, in nature, when a ray of light passes near a massive object, it appears to bend, as if gravity were pulling it. But what's actually happening is that the ray of light is following a geodesic, which is the straightest possible path in the curved spacetime. In other words, the ambient space around that mass. So that's the very definition of a straight line in this particular ambient space. From our perspective, in flat space, the path looks curved. But to the light itself and to any observer living within that curved region, the path is still straight. Mathematically, this is exactly what an embedding captures. The light's path remains straight intrinsically, even though it appears extrinsically curved when embedded into a larger reference space. The underlying idea here is Gauss's famous theorema egregium, or remarkable theorem, which says that intrinsic properties do not depend on how the source space sits inside of an ambient or target space. Some examples of intrinsic properties are the Ricci curvature, distances, angles, geodesics, areas, volumes, and even expansion rate. One of the key requirements for a property to be intrinsic is that it must be derivable only from the metric g mu nu of the space. In other words, from the internal ruler that allows us to measure distances, angles, and curvatures without relying on how the space is embedded in any higher dimensional setting. For example, we don't need to travel all the way to space and look at the Earth from its ambient space in order to see that it's curved. We can simply observe intrinsic phenomena that takes place on its surface, like that the sum of angles of a triangle over large distances is always greater than 180 degrees, that the shortest routes are always great circle paths, not what we would call straight line anymore, and also geodesic deviation, so two initially parallel paths eventually converge at the poles. This implies that the Earth's surface could very well be all there is in the universe, effectively being the universe itself, And even then, we would still be able to note that it has intrinsic curvature. That's exactly what happens to what we currently call the known universe. We can measure its intrinsic curvature and all the other intrinsic properties without ever assuming that it is embedded in a larger ambient space. If you're enjoying this video, don't forget to like it and to subscribe to the channel. By the way, intrinsic properties are very important in physics, because they represent physical characteristics of spacetime that are independent of coordinate systems or embedding choices. In other words, they're invariant under reparametrization, and are the same for all observers, which makes them perfect for expressing physical laws.
As we said earlier, expansion rate is one of these intrinsic properties of a space. When astronomers observe galaxies moving away from each other, they are measuring an intrinsic property of the universe. So, even if we have no idea whether the universe is embedded in a higher dimensional reality, or whether there is no outside at all, we can still say with confidence that it is expanding. That's the power of mathematics. It allows us to describe the behavior of the universe from within, even when we can't possibly visualize it. Of course, our brains are so used to perceiving the three-dimensional world around us that we have a hard time trying to imagine a universe that sort of expands on itself. This is the mathematical formula that describes the expansion of our universe. Rho is the matter energy density. K is the curvature parameter. Lambda is the cosmological constant. And A is the scale factor, which depends on time, t. So the scale factor changes over time. Its first derivative, or rate of change, is what we call the expansion rate of the universe. Let's see a simplified illustration of how the scale factor A works. We start by defining a two-dimensional square manifold, where each point is labeled by two intrinsic coordinates, x and y, ranging from 0 to 1. Notice how this coordinate system does not extend to points outside of the square, since it's not supposed to be embedded in a higher dimensional space. And that's why these coordinates are intrinsic. Actually, this representation itself is flawed. And this is so because there is no ambient space to begin with. In order to really study only intrinsic properties, we should view the square covering the entire screen, since it's all there is. Unfortunately, this is technically impossible because YouTube's screen is rectangular, but you get the idea. Now let's define a metric in it. In other words, a ruler to measure distances and angles. This metric describes a flat space, but with a time-dependent scale factor A of t in it. Here, ds is the infinitesimal proper distance between neighboring points. In order to make the example more concrete, let's define a linear scale factor explicitly. This means that at time t equals 0, the square has side length 1. At time t equals 1, a of 1 is 3. So all distances are tripled. At t equals 2, a of 2 is 5. And so all distances are 5 times longer than at the beginning, and so on. This universe is expanding at constant speed. By the way, our actual universe is not expanding at a constant rate, but actually at an increasing rate. This means that the expansion is speeding up. The distances between galaxies are growing faster and faster. In mathematical terms, the second derivative of the scale factor A of t is positive. Actually, in some really distant parts of the universe, galaxies are moving away from us faster than the speed of light. Not because they are speeding up through space, but because space itself is stretching. Back to our toy model of the universe. Let's take 2 points, P and Q. Their coordinate separations are dx equals 0.5 and dy 0.25. Therefore, the so-called proper distance between points P and Q, when using the metric, is this. d of t, or ds in this case, is a of t times the square root of the two measures, dx and dy, each one of them squared. After calculating everything, we find this expression, which is linear. As mentioned earlier, the expansion rate is calculated with the derivative of the scale factor with respect to time. So taking the derivative of 2t plus 1, we get 2. And therefore, for each second, the distance between all points increases by a factor of 2 per unit distance. Notice how we calculated the expansion rate without ever referring to any ambient space, just in terms of intrinsic properties. In conclusion, the expansion of our universe doesn't depend on the existence of a sort of larger ambient space around it. We know that the universe is expanding because we can observe experimentally that galaxies are moving away from each other. And this is done through a physical phenomenon called redshift. And all that is required are measurements of purely intrinsic properties. In conclusion, what is the universe expanding into? Mathematically speaking, nothing. The expansion we observe, the one that we can measure and calculate, is an intrinsic property of the manifold that we use to model spacetime. It's not a movement into an outside void. We saw many types of intrinsic properties here, and one of the things they have in common is that they are all derivable from the metric tensor. So, at the end of the day, that's all we care about, and the universe is not expanding into anything else. Chapter 16. Differential forms. In calculus, we're used to derivatives telling us how fast something changes, but only in one direction at a time. What we really want though, especially in abstract curved spaces, is a way of describing how something changes in any direction we choose, and to do so in a way that respects the geometry of the space. This is where differential forms come in. A differential one form lives at each point on a surface, and it's just like waiting for you to handle it a direction, like a vector, so that it can tell you how fast something, like temperature for example, is changing in that direction. But forms can be extended way beyond just telling you rates of change, because they can extract components, detect orientation, and let us even integrate over surfaces, or other curved spaces. We'll talk about dual spaces here, tangent spaces, cotangent spaces, and we'll build the intuition from scratch. We'll start with one forms and we'll build up to m forms. Imagine you're hiking across a smooth hill landscape. This landscape is your space. You can walk in one direction from any point. But let's forget about embedding it into a three-dimensional space. Just focus on the ground under your feet. No up or down direction. Now, suppose that at every point on the surface, there is a temperature assigned to it. The higher up you are on the hill, the hotter it gets. It's important to notice that temperature is just a real number. It doesn't have any direction associated with it. This is the concept of a scalar function, denoted as t in this case. You stand on a point and look around. At that moment, you're standing on a spot that has a temperature value, say 80 degrees Celsius. What can you measure? If a specific direction is given to you, you can take a tiny step along it. This little displacement can be measured with a vector. However, it says nothing about what's changing in the environment. It's also important to note that the vector cannot be represented this way, sticking out of the floor, since there is no external ambient space. We also can't just draw its sort of shadow on the floor, because vectors do not bend like that. The vector actually lives in a different separate space, called the tangent space. If the hill landscape is called M, which stands for manifold, then the vector V, based on the point P, lives in the tangent space TPM, which is specific for this point. Now, think about what a simple derivative does. It measures the rate of change of something, like temperature, with respect to something else, like distance, but only as you move along a straight line, usually the x-axis. For example, if you move east, the derivative might tell you how fast the temperature changes per meter walked. That's great! But it does so only in one specific direction, not in general. However, wouldn't it be nice if we could somehow combine the best of both worlds? In other words, the directionality description of vectors and the capacity of tracking rates of change of scalar fields. That's what a directional derivative does. It requires both a scalar field and a direction, and it gives you back a number. Like, you'll feel the temperature increase at a rate of 30 degrees Celsius per meter in the direction you're heading. A directional derivative is often expressed this way. It reads as, the rate at which the scalar function t changes as you move in the direction of v is given by feeding the vector v into the one-form dt. Okay, but what is a one-form? A one-form is a mathematical object that eats a vector, so a direction, and returns a real number. However, it's important to emphasize that dt on its own, with no vector attached to it, is not a real number. It's more like a mapping, or a machine, that takes in a direction and tells you how the function t is changing along it. That's a one-form. Attention, that doesn't mean that one-forms and directional derivatives are the same thing, but rather that they're very closely related. More specifically, a one-form is a generalization of a directional derivative. The directional derivative dvt is the specific result you get when you choose a scalar function t, choose a point p on the manifold, choose a direction v, and ask the question, how does t change as I move in the direction v from p? It is a number. The one-form dt, on the other hand, exists before we've chosen any direction. It lives at every point on the manifold. It takes any direction we give it and tells you how the function is changing in that direction.
Let's see a concrete example. A scalar field t from m to the real numbers will be defined as x squared plus y squared, where m is a two-dimensional manifold, so a surface. This function gives a temperature at each point. Pick a point p equals to 1. At this point, the temperature is 5 degrees Celsius. What happens to the temperature if I move only to the x direction? Well, let's see. Therefore, as you can see, for every unit you walk east, the temperature increases by 4 degrees Celsius. What happens if you move only in the y direction? Using the very same logic, we find this. Therefore, for every unit you walk north, the temperature increases by 2 degrees Celsius. That's great, but what about moving diagonally? Let's say 45 degrees north and 45 degrees east. Now we need to define a vector v that will encode this direction. Actually, this expression makes no sense at all in this context, because we're assuming the manifold M to be abstract. In other words, possibly curved and not embedded into a higher dimensional space. So we cannot use the basis vectors I and j of calculus in order to write the vector v as a linear combination of them. Visually, we're saying that the tangent vector v cannot stick out of the manifold. It needs to live inside of its own tangent space, TPM. As a consequence, we need a new pair of basis vectors that are capable of spanning the entire tangent space at a point P, such that any tangent vector v in TPM can be described as a linear combination of them. In differential geometry, we define tangent vectors as derivations, because we don't have a global ambient space. This is a hard concept to grasp, and is usually one of the greatest sources of confusion when people are trying to learn differential forms. So pay close attention. Instead of defining a vector by its direction in space, we define it by what it does. A tangent vector tells us how a function changes at a point. And this is exactly what a derivation does. The goal is to describe it only in terms of intrinsic properties. The differential operator partial x does exactly that. It takes a function f and returns the rate of change in the x direction. Hence, the vector v is described as a linear combination of partial x and partial y, which are not only considered differential operators in this context, but also vectors themselves. More precisely, the pair partial x partial y is the basis of the tangent space TPM, and therefore the appropriate picture you should have in mind is this. So, vectors themselves are considered differential operators when dealing with abstract and curved spaces. Back to our example, we can apply the one-form dt to this diagonal direction given by this vector. The coefficients square root of 2 over 2 come from the fact that the sine of 45 degrees and the cosine of 45 degrees are both square root of 2 over 2. Remember, a one-form is a mapping that takes vectors and returns real numbers. Since the vector v is an operator, we can act it on the scalar function t, which is literally the definition of directional derivative. Thus, we can also write it in terms of the result of acting the one form on the vector v. So the question is, what does dt look like before acting on the vector v?
Well, what about this? It turns out that this expression for the one-form dt works perfectly. If you want to see the detailed explanation for why this is true, check out the PDF link in the description, where you'll also find a very nice summary of the entire video. In order to see that this is the correct expression of the one-form dt, though, we have to assume that these terms dx partial dx and dy partial dy are 1, and at the same time that dx partial dy and the opposite of it are 0. But how come this is true? Well, we've seen that partial x partial y is the basis of the tangent space TPM for a point P in the manifold. But what about dx and dy? What do they represent? dx and dy are covectors and also one-forms. Indeed, a covector is the same as a one-form. When we refer to it as a covector, though, we're usually in the context of linear algebra. Just to give you guys a taste of it, when you have basis vectors e1 and e2 with subscripts, no matter if they are orthogonal or not, you can find mathematical objects denoted as covectors e1 and e2 with superscripts, such that e1 subscript is perpendicular to e2 superscript and so on for the opposite, but not to their respective counterparts. So these relations are valid. And this fact can be expressed in a more compact way as this. EI subscript times EJ superscript is the Kronecker delta, so basically the identity matrix. And that's precisely what's going on here. Partial x is perpendicular to dy, and so on for the other terms, using them as basis vectors and basis covectors. These relations are valid strictly in the sense that their multiplications give us 1 or 0 accordingly. So the covectors dx and dy form a basis for a space that is dual to the tangent space TPM. This dual space is called cotangent space T star PM. This is not actually what it looks like geometrically. It's just a visual representation of the linear algebra facts that we've seen before. In differential geometry, though, dx and dy are referred to as one-forms, and therefore they act on vectors v in order to return a scalar. For dx, this scalar or number is exactly the value of the directional derivative of the function x, or f of x equals x, in the direction of the vector v. A similar result is valid for dy. So the one-forms dx and dy are a sort of filter that extracts the x and y components of a vector. When dx acts on the vector v, for example, we get the magnitude of the vector's projection onto the x-axis, and similarly for dy. Differential forms are especially useful in very abstract and curved spaces, because they don't rely on an ambient space or coordinates, or even a precise notion of distance, like a metric. Instead of describing geometric objects as like arrows in space, forms describe how scalar functions change. They act on vectors and extract quantities like rates of change, flux, and orientation.
And forms do all of it in a way that's 100% intrinsic to the space. That's why they're perfect for studying manifolds, even if some local regions are twisted, curved, or stretched, and even if global coordinates don't exist. So to recap, the symbols partial x and partial y represent the basis vectors of the tangent space TPM at a point P on a manifold. They describe directions of motion along the x and y coordinates that are intrinsic to the manifold. Their duals, dx and dy, form a basis for the cotangent space T star PM, which consists of linear functionals, also known as one-forms, that act on tangent vectors. This dual pairing is what allows us to write and compute geometric quantities. A vector v is expressed as a linear combination of the basis vectors, and a one-form, like dt, is expressed as a linear combination of dx and dy. When we apply the one-form to a vector, the result is a scalar, so a measurable quantity, like the rate of change, which reflects how much a vector points in the directions given by the one-forms. Let's finish this topic by applying the one-form dt, with t being x squared plus y squared, to this vector v at a point p equals 2, 1. For more details, check out the PDF link below. Therefore, for every unit you walk northeast, the temperature increases by 4.2 degrees Celsius. Before moving on to two forms, let's generalize the definition of a one-form for manifolds of any finite dimension. The dimension of the tangent space TPM is the same as the dimension of the manifold. Let's say n.
The basis of the tangent space TPM is partial x1, partial x2, and so on up to n, the dimension of the manifold. Or simply, we can write partial 1, partial 2, and so on up to n. The cotangent space T star PM, so its dual, is the space of one-forms at the point P. Its dimension is also n, and its basis is dx1, dx2, and so on up to n. From the definition of dual basis, this relation must always be satisfied, just as before. Thus, what is a one-form on this abstract manifold M? A one-form, which is very often denoted as omega p, is a mapping that assigns to each point P in the manifold a linear mapping. In coordinates, any one-form can be written as this, where the coefficients ai are smooth functions on the manifold M. Awesome! We're ready to move on to two-forms. A two-form is a function that takes two vectors and returns a number. So now we go from two copies of TPM to the real numbers. But there's a caveat here. The order of the vectors matter. This property is called antisymmetry. In order to deeply understand antisymmetry, think of vectors v and w at the point P forming a small parallelogram. When a two-form omega, which can be written in coordinates as dx wedge dy, acts on those vectors, it measures the signed areas of that parallelogram. So not just how much area it spans, but which way it is oriented, positively or negatively. Swapping the input vectors flips the sign of the result, and it produces a reversal in orientation according to the convention you pick. This property is super useful because it gives us a sort of detector of local orientation on the manifold. Now, you must be wondering, what is this symbol? This is called the wedge product, and it's what allows us to construct high-order differential forms, like two forms, using one-forms as building blocks. Think of it like this. Just as adding vectors give a new vector, wedging two one-forms gives us a mathematical object that knows how to handle two vectors and return a scalar. However, just as we said before, in an antisymmetric way. Since two forms measure oriented areas, guess what area the wedge product of a basis vector with itself measures? dx wedge product with dx is just 0. Let's see what happens when the two forms dx wedge dy acts on the vectors v and w as the basis vectors of the tangent space TPM. The result is +1, because the orientation agrees with the order of the wedge. First dx, then dy. If you flip the order, in other words, dy wedge dx, the result is -1. Now we generalize two forms to n dimensions. This is an antisymmetric bilinear map that takes two tangent vectors at a point P and returns a number. In local coordinates x1, x2, and so on up to xn, the basis for two forms is built using wedge products of one forms. We know that there are n factorial over 2 factorial times n minus 2 factorial such basis elements in total, and general two forms looks like this. We could also think about generalizing it to m forms in n dimensions. This is a totally antisymmetric multilinear map that takes m vectors and returns a number. Each m form is written in terms of wedge products of m distinct one forms. So the basis of the space of m forms at point P is dxi1 wedged with dxi2 and so on up to im. In total, there are n factorial over m factorial times n minus m factorial such independent m forms. To recap and conclude, this is a table that summarizes everything we've seen in this video. So differential forms let us calculate how things change along directions, even on curved spaces. They act on vectors and return real numbers, like rates of change, for example. And that's why they are so powerful in geometry and in physics. Chapter 17, Geodesic Equation. In curved spaces, straight lines don't look so straight anymore. The geodesic equation captures exactly this idea. What is the straightest possible path between point A and point B in a curved space? And it does it by extremizing or minimizing, in some cases, the distance between 2 points. What does it mean for a vector to stay parallel to itself as it moves? That's where covariant derivative, and in particular, the Levi-Civita connection, come in. They give us the precise mathematical tools to understand how vectors change, especially when they are transported from one point to another in a curved space. In this chapter, we'll understand the meaning of the geodesic equation, we'll understand its importance, and its highlight will be the fact that we'll see 5 different methods for solving it. Solving the geodesic equation is really important, because it can allow us to predict orbits of particles around massive objects, where spacetime is curved. This is the list of the best analytical methods for solving the geodesic equation. In pure mathematics, the geodesic equation is one of the core concepts in differential geometry. It encodes the notion of the straightest possible path on curved spaces, and without it, it's impossible to truly understand the geometry of any particular manifold. In applied mathematics, its power is even more evident. For example, it describes particle trajectories in general relativity, light propagation in optics, and optimal paths in navigation and robotics. That said, solving it exactly is usually really tough, but when the geometry allows, we can use some very powerful analytical tools that make the problem much simpler. Let's see the first of the top 5 analytical methods for reducing its complexity and find exact solutions. First, symmetries and killing vectors. As the name gives away, this method explores symmetries in the geodesic equation and in the space you are studying, and it does so by using very important mathematical objects called killing vectors. A killing vector is a direction you can move in without changing distances in the space, no stretching or contracting along it. We won't get into details here, but more formally speaking, a killing vector is a vector whose flow preserves the metric. The distances and angles remain unchanged along it. If you'd like to be the first to find out when we launch our very first books and courses, sign up with your email address in our homepage. The link is in the description. Let's get back to the video now. Before we dive deeper into this first method though, let's quickly recall what a geodesic equation actually is. In differential geometry, a geodesic is a curve whose velocity vectors, so its tangent vectors at each point, stay parallel to itself as you move along it. In more formal terms, it's a curve gamma whose tangent vector gamma dot satisfies this relation, with this symbol representing the Levi-Civita connection, which is just one of the many types of covariant derivatives. A covariant derivative measures the infinitesimal rate of change of a vector field, taking into account the manifold's curvature. The subscript in the Levi-Civita connection tells us to measure that change in the direction of the curve's own velocity vector. This equation is basically telling us the tangent vector to the curve has zero change in its own direction. It's parallel transported along the curve, in other words, no change at all. The vector stays parallel to itself along the entire curve gamma. It's important to mention one thing that got me really confused when I learned these concepts for the first time years ago. Gamma is the path, or curve, in the manifold M. Gamma dot is the velocity vector at a point P in the manifold. So the vector that is not only tangent to the manifold, and therefore lives in the tangent space TPM, but it's also tangent to the curve gamma itself. This is different from a random vector v in the tangent space TPM, and as a consequence, the magic of getting zero in the right-hand side is not guaranteed anymore, even if you are transporting it along a geodesic path gamma. The opposite is also true. If you consider the velocity vector of a geodesic curve gamma, so the vector that is tangent to the manifold and to the geodesic gamma itself, and parallel transport it along any other random direction given by a vector v from point P to point Q, the vector does not keep its original direction necessarily. The vector gamma dot, then, can be written as a linear combination of the basis vectors of the space where it lives. And since it lives in the tangent space, the basis is partial partial x1, partial partial x2, and so on up to n, or simply partial partial xi, where I runs from 1 to the dimension of the manifold. Now we need to figure out what the components of this linear combination are. Well, let's go back to first principles. What is the curve gamma? It's just an infinite set of points in the manifold that, when put together, form a smooth continuous path that we can parameterize with t in the real line. Gamma dot is just a notation to its differential with respect to the parameter t, or time if you will. And since gamma is just an infinite set of points in the manifold, we can write it in local coordinates as this. And therefore, gamma dot, written in the basis vectors of the tangent space TPM, becomes x dot superscript I partial partial xi. Great! Just to remind you guys, our goal here is to use this definition of velocity vector, gamma dot, of the geodesic path gamma in the equation nabla subscript gamma dot acting on gamma dot equals 0. All we have to do now is find a way of writing down explicitly the Levi-Civita connection. The Levi-Civita connection can be seen as a mapping or an operator that acts on a vector. That's where we insert this vector, in these slots right here. It's important to say that the way we wrote it here is not standard, and you will probably not find it written this way anywhere else. But it does help us to understand how this operator acts on vectors. This is one of the slots where you're supposed to plug in your vector v. This partial term differentiates the components vk of the vector field. Now, this term means move the vector v in the direction of the path's velocity. And finally, the Christoffel symbols correct for the fact that the basis vectors themselves change as you move because of the manifold's curvature. Since we want the vector v to match the velocity vector gamma dot of the geodesic gamma, we get this expression instead. But what is gamma dot superscript I? This is the ith component of the vector gamma dot. In other words, just x dot superscript I. And if all of it is 0, according to our geodesic condition, then this term, which is just a component of the vector, must be 0 as well. And that's the famous geodesic equation. We finally got it. That's precisely the equation we want to solve. For more details, check out the PDF link in the description. Now we'll go all the way back to our first method, but Sophia is going to be the one to tell you guys about it.
First, symmetries and killing vectors. Just to recap, we'll use mathematical objects called killing vectors in this method in order to explore the symmetries of the manifold and solve the geodesic equation. A killing vector is a vector field whose flow preserves the metric, no stretching or contracting along it, even though the manifold itself does so, because of curvature. Just to help you guys better grasp the abstract notions we're about to deal with, let's see what these killing vector fields could represent in physics. For example, more specifically in the spacetime manifold. 1. Time translation symmetry. Energy conservation. The killing field is partial t, or simply partial t. If the metric, so the spacetime geometry, does not depend on the time t, then time translations from t to t plus epsilon are a type of symmetry. The killing vector field, partial t, points along the time direction, and it can also be expressed as this. The only non-zero component is in the time direction. For more details on how we work with this vector once we identify it, check out the PDF link in the description. It's really interesting. Anyway, there are other killing vectors as well. Spatial rotation symmetry, angular momentum conservation. Suppose that the geometry is invariant under rotations around some axis, say the z-axis. Then, this killing field is the generator of that rotation. This killing vector expresses an infinitesimal rotation in the xy plane. If you want to see these killing vectors in action, together with other examples as well, check out the PDF link in the description. Second, first integrals / conservation laws. Imagine we have a manifold with this metric. Out of all possible paths connecting points A and B on the manifold, there is one that is the straightest possible curve. Using the principle of least action from variational calculus, we can derive the Lagrangian of the system, which will allow us to find the geodesic path we want. Think of the Lagrangian as a measure of the cost of a path, and the geodesic is what you get once you minimize the total cost, which is the action of the system and is built from the Lagrangian. There are two natural sources of conserved quantities. The first, energy-like quantity. When the Lagrangian does not explicitly depend on the parameter t, which is often interpreted as proper time in physics, then there's some quantity here that's being conserved. This result is called Noether's theorem. The conserved quantity here is identical to the Lagrangian, but is interpreted differently. When studying mechanics, this is the usual physical energy of the system, but in purely mathematical terms, it is a constant that classifies geodesics as time-like, so E is less than 0, null, so E is equal to 0, or space-like, E is greater than 0. There are more details about how these definitions and technicalities are crucial for solving the geodesic equation, but to keep this video digestible, we've added them in the PDF link in the description. There, you'll also find a concrete example in which we apply the Lagrangian formalism in order to simplify the geodesic equation a lot, and as a consequence, find solutions. Let's see the second natural source of conserved quantity, before moving on to the third method. Second, cyclic coordinates, or generalized momenta. When the Lagrangian doesn't depend on a specific coordinate xk, just like in our case here, then this quantity pk is conserved. It's called the conjugate momentum, or generalized momentum. Every coordinate, x1, x2, and so on, up to xn, has an associated conjugate momentum. From the physics point of view, if a coordinate xk does not appear explicitly in the Lagrangian, like in our case, then moving along any coordinate direction doesn't change the cost. This symmetry implies another conservation law, once again because of Noether's theorem. Okay. But how does it help us to solve the geodesic equations? Well, it simplifies them a lot. As an illustration, the geodesic equations on the sphere S2 are these. This is a coupled system of second-order nonlinear ODEs in the variables theta and phi. They are difficult to solve directly because both coordinates interact through trigonometric functions. After applying the Lagrangian formalism that we talked about here, we reduce the problem to this equation instead. Again, check the PDF link for details. Which is a first-order ODE in a single variable theta. It eliminates the coupling with phi and simplifies the problem a great deal.
Third, separation of variables. This is probably the physicist's favorite method for solving differential equations, because of its simplicity. Unfortunately, however, it rarely works, because it requires some very special conditions, such as the possibility of rewriting the partial differential equation in such a way that both sides, so the left-hand side and the right-hand side, depends only on one variable. If it's not possible, you might need some more sophisticated techniques, like Fourier analysis, Green's functions, or numerical methods. Anyway, we covered it in detail in the PDF link. Here though, we'll see it directly applied to the geodesic equations of the sphere. As we've seen before, these are the geodesic equations of the two-sphere. Just as a reminder, geodesics in this manifold are great circles. Let's try to separate variables. Consider the second equation and rewrite it as this. Now, define u as phi dot, and therefore the second derivative of phi with respect to t is just the first derivative of u with respect to t. Rearranging the terms, we get this equation. Now, pay attention because this is the part where we separate variables. Notice how the left-hand side depends explicitly only on u, and the right-hand side depends explicitly only on theta. We can integrate both sides, and this is the final result we get. However, we still need to know theta of t from the first geodesic equation in order to calculate this integral explicitly. For example, pick theta of t as pi over 2. And thus, with this choice of theta of t, we get that phi of t is c1 times t. c1 here is interpreted as a constant angular velocity, also represented as omega. This solution is a great circle. Fourth, coordinate transformations. The idea here is that sometimes the geodesic equations look very messy and confusing in one particular coordinate system, but they simplify drastically in another one. So instead of suffering through trying to solve them directly, you can just perform a clever change of coordinates. Think of geodesic paths as geometric objects, in the sense that they only depend on intrinsic properties of the manifold, like all the quantities that can be derived from the metric, including the metric itself. So geodesics are independent of coordinates, which is great news for us. You can have the same geodesic equation, but when written in different coordinate systems, they look completely unlike, even though they are actually describing literally the same geometric object. Just to illustrate it here, we did it with the two-dimensional hyperbolic plane in the PDF link in the description, and that's what we got. The first set of geodesic equations is super hard to solve. The transformation of coordinates used here was the famous Poincaré half-plane xy with y greater than 0. I know, looking at this set of geodesic equations, we see that it is not trivial at all. Just as before, we have a system of non-linear second-order ODEs, but the structure is much simpler. There are only rational functions involved here, like 1 over y. No crazy things like hyperbolic sine or hyperbolic cosine. The geometry is much simpler as well. In the half-plane model, solutions are just vertical straight lines, when x is constant, and semicircles orthogonal to the boundary at y equals 0. Fifth, integrability and quadrature. The quadrature method is about avoiding the direct attack on the second-order geodesic ODEs, which are usually nonlinear and messy. Instead of working with the geodesic equations themselves, we notice that geodesics come from a variational principle. They are the curves that extremize the length functional. This means that they can always be described by a Lagrangian that can be built from the metric. Once we have the Lagrangian, we don't need to solve the ODEs directly. Instead, we look for conserved quantities, like energy, angular momentum, linear momentum, and so on. And all of them come from symmetries of the system. Okay, so far this sounds pretty much the same as the method we've seen before. But here's the difference. Once these conserved quantities are written down, the system can often be reduced to a first-order equation. At this point, we can rewrite it in the form d theta dt equals f of theta, and then integrate it. That's the meaning of the word quadrature in this context, to turn the problem into an integral. The solution may not look simple, because it often involves elliptic or other special functions. But the point is that the problem is completely solved in principle, because the geodesic is fully determined by these integrals. In our sphere case, for example, the metric is this. The energy conservation gives us this equation. And we need to rearrange it in what is called quadrature form. Once here, we can integrate both sides. After a lot of calculations, we get this crazy expression for theta of t, which I believe can be simplified. If you guys find a way of doing so, please let us know. That's the first one. The second, using a similar approach, gives us phi of t. So the geodesic equation, among other things, gives us the straightest possible path. And when we find its solutions, it can give us something very important, which in some contexts, it's the orbit of particles around massive objects in general relativity. Chapter 18, Tensor Impostors. Not everything that looks like a tensor is really a tensor. It's very easy to look at an object, see subscripts and superscripts, and think, this is a tensor. But actually, they can be what I call a tensor impostor, because they failed the most important test, which is to transform consistently under a change of coordinates. This chapter is about learning how to detect tensor impostors. At the heart of the issue is the idea of intrinsic meaning. As you can tell by now, we use this word intrinsic a lot here. And that's because this is really the core of differential geometry. You need to look for intrinsic properties of the manifold. A true tensor carries physical and geometric information that remain valid no matter what kind of coordinates you choose. It doesn't mean that the tensor components stay the same, but the rules for changing them, so the tensor transformation rule, preserve their meaning. Can you tell which of these mathematical objects are tensors and which are tensor impostors? Before answering this question, we need to define what a tensor is and what we mean by tensor impostor. A tensor is just a mathematical object that lives on a space, like spacetime or a curved surface, for example, and has a rule that tells it how to stay the same when you change the way you are looking at the space, so when you change coordinates. Think of a tensor as something whose values may change, but its meaning doesn't, no matter which coordinate system you're using. Even more concretely, say you are measuring something physical, like a force, a flow, or curvature, and hand your results to someone who uses a different map of the world, different axes, different rules. If they recalculate your values using the correct transformation rule, they will get the same physical results from their own perspective. A tensor impostor is a mathematical object that really looks like a tensor, especially because of the way it's written, with subscripts and superscripts. But when it comes to transforming it from one coordinate system to another, it fails to be consistent. That's why they're tensor impostors. Their values are coordinate dependent in a way that breaks the idea of being the same in all coordinate systems. You'll often hear people saying, a tensor is an object that transforms like a tensor. I mean, this phrase is not very useful. I remember the very first time I heard a professor at my university saying something like that, and I'd be more confused than before. The problem is that they are defining a tensor using the notion of tensor transformation, which is weird because if a student doesn't know what a tensor is, that's why we're trying to define it, right? Then they probably wouldn't know what a tensor transformation is as well. So what do people actually mean by this sentence? Well, let's see a concrete example of a tensor transformation. We want to pick a candidate for a tensor, write it down in local coordinates, and transform it to a new coordinate system. Then we take the original candidate once again, transform it using the tensor transformation formula that we will see in a moment, and finally compare the two results we got from two different methods. If they match, then we have a legitimate tensor. Otherwise, we just detected a tensor impostor. In other words, this is a coordinate-dependent object, not intrinsic, not fundamental. Let's pick a simple flat two-dimensional space with Euclidean metric. We can also write it in this form, using the summation convention for matching upper and lower indices. It's important to notice as well that in the matrix version of it, we name the components in the following way. So applying the summation convention for these components, we get that the metric can be written as dx squared plus dy squared. Nice! Now we want to see the problem from a different perspective. We want to perform a coordinate transformation from Cartesian to polar coordinates. The formulas that translate the coordinates xy into r theta are these. Notice that the space is still the same. The only thing that changed was the grid we picked to measure things in it. The most fundamental characteristics about this flat sheet cannot change during the transformation. We usually call these unchanged characteristics intrinsic properties. A good definition of intrinsic property is any geometric object or quantity that can be derived from the metric, including the metric itself. In simple terms, the metric or the ruler we use to measure distances is the most fundamental geometric feature of a space. So going back to our metric, dx squared plus dy squared, we can use the substitution for polar coordinates in it. Okay, but what do we do with these guys now? Sophia will tell you about it.
Well, these are differential one-forms, and they can be expressed in the new local polar coordinates using the chain rule of multivariable calculus. After working on all the derivatives and simplifications here, we find that the same metric written in polar coordinates is this, or in matrix form, this. Back to our example. We basically performed a coordinate transformation to express the same identical metric in two different local coordinate systems. But the question remains, is it a legitimate tensor? And the answer is given by the formula for a legitimate tensor transformation. Failing to satisfy this equation would automatically disqualify an object as a candidate for tensor. Let's analyze each term. Gij is our original metric, before the coordinate transformation. In our case, G prime alpha beta is the same metric, but after the transformation. Xi are the original coordinates, x1 is x, and x2 is y, for I equals 1 or 2. Same thing for xj, with j equals 1 or 2. X prime alpha and x prime beta are the new coordinates r and theta for alpha and beta 1 or 2. The expectation is that after using the tensor transformation formula for the original metric in Cartesian coordinates, we get as an output the actual matrix in polar coordinates. If this fails to happen, then we just detected a tensor impostor. We tried it out in the PDF link that you will find in the description of this video, and after a few calculations, we got exactly the same result as before. Therefore, the metric tensor is indeed a legitimate tensor. Let's try the same identical thing with this object, partial mu v nu, which is just the partial derivative of a vector field. So the rate of change of the components of a vector field defined throughout the manifold at each point, and living in the tangent space dPm for each point p in M. This is a vector field defined on a 2D flat plane in Cartesian coordinates xy. To make things less abstract, we pick the specific case in which the vector field is this. Since each of these vectors actually live in the tangent spaces at each point, they can be written as this, where Vj are the components, in this case either x1 equals x squared or x2 equals y squared, for j being 1 or 2, and partial xj are the basis vectors of each tangent space written in local Cartesian coordinates xy. Now we can take the partial derivative of the vector field, component by component. After working on the math, you'll find this matrix that describes each of the 4 possible values of this object, written in Cartesian coordinates.
Good! Now, let's transform it to polar coordinates. First, we need to rewrite the vector field in polar coordinates. This is not an easy task because not only the components are written in a different coordinate system, but the bases of the vectors are also written in different coordinates. And as we know from linear algebra, when we change coordinates, both the components and the basis vectors transform. After expressing the Cartesian basis in terms of polar basis, we can finally write the vector entirely in polar coordinates. Now, take the partial derivative of the components of the vector in order to get our tensor candidate. And we find this matrix describing the object we're studying, but this time written in polar coordinates. Nice. Now the question is it consistent with the tensor transformation rule? We need to check it out. After a lot of calculations, we found a different matrix from before. The conclusion is the partial derivative of a vector field is coordinate dependent. So this object does not obey the tensor transformation rule, and therefore it is a tensor impostor. The partial derivative of a vector field is not intrinsic to the manifold. This is a table of tensor impostors. And this is a table of legitimate tensors.
We really want to encourage you guys to use the methods you've seen here and apply them in order to prove if some of these mathematical objects are legitimate tensors or are tensor impostors.
Not all objects with indices are tensors, and in this chapter we saw exactly why that matters. We saw the tensor transformation rule and how to detect tensor impostors. Recognizing their difference is really important in geometry, but also in physics, because this way you can really understand what are the physical laws that do not depend on your perspective, on the coordinates you're using. Chapter 19. The right side of Einstein's equations. When a mathematician looks at the right-hand side of Einstein's equations, he sees a geometric object, something that lives in a smooth manifold and transforms nicely under coordinate changes. Physicists, though, look at the same thing but see something different. He sees physical quantities like energy, momentum, stress, pressure, and also radiation. It basically gives him a detailed description of the universe at each point in space and time. And the interesting thing here is that both are valid perspectives. And if you can be flexible enough to switch from one to the other according to the problem you're dealing with, I think you're going to have an advantage with respect to others. Learn how to see the stress-energy tensor this way. When looking at the right-hand side of Einstein's field equations, mathematicians and physicists see different things from each other. For the mathematician, this constant is just that, a constant. He's not interested in the fact that it involves two of the most fundamental quantities in nature. In other words, the gravitational constant g and the speed of light c. So the mathematician sees it as nothing but a scaling factor that might as well be called kappa, for example. This tensor, T mu nu, is described as a rank 2 symmetric object, two indices, defined on a differentiable manifold. It is defined pointwise. Its components vary smoothly with the coordinates, and it is covariant under coordinate transformation. It doesn't depend on the local coordinate choice. It is an intrinsic geometric object. The mathematician would also describe this tensor as a bilinear mapping, so a function that takes two tangent vectors at a point on the manifold and returns a single real number. This real number, the output of the bilinear map, is not interpreted as energy or momentum, as a physicist would, but instead it's viewed mathematically as encoding a relation between directions on the manifold at that point. The mapping is smooth, and so we can differentiate it and contract it with other tensors. Each one of these operations would produce a different result that directly influences the left-hand side of Einstein's equation. In other words, the geometry and curvature of spacetime. Now, the physicist would see the situation from a different perspective. Each component represents something tangible: energy, momentum, pressure, radiation. It tells you how matter moves, how it pushes and pulls, and how it exchanges energy. This tensor encodes the state of a fluid, a beam of light, an electromagnetic field, or even the vacuum. but always in terms of observables, measurable quantities. That's a very common misconception, that only matter is capable of bending spacetime and producing curvature. This tensor tells us a different story. Stress, which is a generalization of pressure including shear and tension, energy in the form of matter or radiation, and momentum, that is energy in motion or flow across space. These are all capable of producing space-time curvature. Interestingly, this matrix encodes all this information, and if at any moment you want to extract a piece of data from it, all you gotta do is contract it with the appropriate basis vectors, or tensors, corresponding to the physical quantity you're interested in. One of the most elegant bridges between pure mathematics and physics comes from a result called Noether's theorem, but Sophia will be the one to tell you guys about it.
Noether's theorem tells us that whenever a system has continuous symmetry, there is a conserved quantity. In the context of Einstein's equation, if the laws of physics, and more importantly the geometry itself, remain unchanged when you shift the coordinate system slightly in space or time. That's called translational symmetry. From this symmetry, Noether's theorem gives us conservation of energy and momentum, which means, for example, that the total energy inside a closed region of space doesn't randomly disappear as you move forward in time, and momentum doesn't magically appear or vanish as you move through space. As a concrete example, imagine a perfect fluid at rest. This is a volume of space that looks exactly the same everywhere and in every direction. There is no motion in space, but there's always motion in time. The energy density ρ is constant. The pressure P is the same in all spatial directions. This uniformity gives us something very powerful, translational symmetry. According to Noether's theorem, this symmetry leads to conservation of energy and momentum. But the story doesn't stop there. Imagine rotating your coordinate system, like spinning your frame of reference. If the geometry and physical laws remain unchanged under such a rotation, that's rotational symmetry. Noether's theorem tells us that the symmetry leads to the conservation of angular momentum. Mathematically, this conservation law emerges when the tensor is symmetric. So T mu nu is equal to T nu mu. T01 is equal to T10, and T02 is equal to T20, and so on. Basically, these triangular regions are the same. These components encode information about shear stress, which tells us how the motion in one direction affects neighboring layers. These components represent momentum density in each direction. Think of it as the amount of push from either matter or radiation contained within a tiny volume of space and in a specific direction. And these give us the energy flux, so in other words, how much energy is moving through space in each direction. Notice that for us to have this kind of symmetry, so rotational symmetry, the momentum density must be equal to the energy flux. It means that the amount of energy that is flowing in the spatial direction must be the same as the amount of momentum stored in that direction over time. This balance is what ensures angular momentum conservation. And lastly, in general relativity, we deal with curved spacetime, which means that we must go beyond flat translations and rotations. Here, the symmetry is much deeper. It's called general covariance. Actually, Einstein originally named his work Theory of Invariance, referring to this type of symmetry, also known as diffeomorphism invariance. It means that the equations of physics and the geometry itself look the same in any coordinate system you choose. This symmetry doesn't lead to a global conservation law, but to a local one. Mathematically, it tells us that this tensor must satisfy a sort of geometric divergence-free condition, expressed as this. Intuitively, it means that energy and momentum are conserved locally, from point to point, even when the manifold is curved. More concretely, imagine a narrow beam of light traveling in the x direction, like a laser. This is a classic example of what's called a null dust. A stream of massless particles, such as photons, all moving together at the speed of light. The tensor for this system stores information about how energy and momentum are distributed and how they flow through spacetime. this is the energy density present at that point in space. This one is the momentum density in the x direction. And this is the energy flux. And this right here is the pressure in the x direction. So the amount of force per unit area being exerted on a surface perpendicular to the x-axis. All the other components are zero, since the light beam is not moving along the y or the z directions. And there's no pressure or shear in those directions anyway.
If you want to see the detailed calculations, which are not very long, of the local conservation condition in flat space, check out the PDF link in the description. There you'll also find a summary of the video. Also, if you want to be the first to know when we release our books and courses, sign up with your email on our website, link in the description. In conclusion, the energy momentum tensor captures matter, energy, stress, pressure, and radiation. Whether you approach it as a physicist or as a mathematician, the tensor tells you the content of the universe or the space-time you're dealing with. Chapter 20. The main solutions to Einstein's field equations. Einstein's equations are absolutely the most important thing you can learn in general relativity, and also how to find their solutions, which are metric tensors. They describe how matter and energy shape the geometry of spacetime. At first glance, it looks like just one equation, but actually there are 10 interrelated equations here. Even in the absence of energy and matter, these equations also produce solutions. In this chapter, we'll learn how to understand Einstein's equations by breaking down each one of its components. We look at the key solutions like Minkowski and Schwarzschild spacetimes, which show the geometric role of each one of the tensors involved. Let's begin with something surprisingly simple. You're walking down a hill. Gravity pulls you down. You stumble and fall on your face. Sorry about that. Your body will definitely obey the geometry of the hill, and ultimately of the Earth itself. Einstein's equations describe how space and time themselves curve in response to matter and energy. But here's the weird thing. Even if we remove all matter and energy, these equations still have solutions. Theoretically, these equations could describe entire universes, not just one, but infinitely many. So how many solutions are there to Einstein's field equations? The honest answer is, we don't know. But we do know this. This number is huge, probably infinite. Einstein's equations are 10 interlinked nonlinear partial differential equations. Actually, there should be 16 of such equations, since each side has rank 2 symmetric tensors, meaning it has 2 indices, mu and nu, and is symmetric under exchange. But only 10 of such equations are independent because of this symmetry, which implies that in the matrix representation of these tensors, the components in each triangle here are the same. So all we need to do is count the number of components inside one of the triangles plus the diagonal rectangle. Again, these are the 10 equations. Let's see some concrete examples now. But before that, I would like to say that we attached to the description of this video a document called the Catalog of Spacetime, in which you'll find the most famous solutions to Einstein's equations. Also, if you guys are enjoying the content, please do not forget to like the video and to subscribe to the channel. Let's see the first one, Minkowski spacetime. In Cartesian coordinates t, x, y, z, the Minkowski metric is this. And so the line element is this one. This line element tells us how spacetime itself measures intervals between nearby events. This metric is flat, meaning that all components of the Riemann curvature tensor vanish, which implies that the Einstein tensor is also zero everywhere. This is a vacuum solution of Einstein's equations with lambda equals 0. So the cosmological constant responsible for what we call dark energy is set to 0 everywhere. Let's see the next one now. But before that, if you guys want to help us grow on YouTube, please consider becoming a member of the channel. We really appreciate your support. Second, Schwarzschild spacetime. In spherical coordinates, the Schwarzschild metric is this. We have here the gravitational constant, the total mass of the body that we're studying, and the speed of light. It describes how a massive object with spherical symmetry, like a planet or a star, bends space-time around it, and inside of it as well, as we'll see in a moment. The line element here looks like this. This is also a vacuum solution for T mu nu equals 0. And as a consequence, we have that Einstein tensor G mu nu is also 0. However, it does not mean that the curvature is 0. The fact that the space-time is flat implies that the Einstein tensor is 0. But the opposite is not necessarily true. The curvature is not necessarily 0. In our case, we're describing what happens outside the object responsible for space-time curvature. That's why T mu nu is 0. But curvature itself is not 0. Okay, but what about inside the massive body? Inside, we cannot assume T mu nu to be 0, because there is clearly matter and energy there. Instead, Einstein's equations are often solved by approximating the star or the planet you are dealing with as a perfect fluid. The stress-energy tensor takes this form, where ρ is the energy density, p is pressure, and the terms u mu and u nu are for velocities. This specific stress-energy tensor produced this Schwarzschild interior solution, for which the line element is this. Now, before moving on, there are three important things to notice here. First, a point at infinity. Let's pick a point at infinity and see what happens with the Schwarzschild metric there. As we've seen up to this point, there are two possible Schwarzschild metrics, one for points in its interior and another one for points in its exterior. Since we want to see what happens to the metric at a point at infinity, and we'll see in a moment what that means, then we clearly must use the Schwarzschild exterior metric for r that tends to infinity, and that's what we get. I mean, look at the time and radial entries, which are identical to the ones for the Minkowski metric. It does make sense, since if you move infinitely far from a massive object, its gravitational influence tends to 0. In other words, you find yourself, practically speaking, in a flat portion of space-time. More technically, we would say that at infinity, space-time is asymptotically flat, locally Minkowski in the time and radial components, or directions. Okay, but what about those ugly infinity symbols in the angular entries? Well, as r tends to infinity, the sphere becomes infinitely large. So the metric components for angular directions diverge, simply reflecting the fact that moving a tiny angle at infinity sweeps an infinite physical distance. In the limit, all directions collapse to the same ideal point at infinity, similar to what happens in projective geometry. Don't worry if you've never studied projective geometry before. The intuition is really simple, but very powerful at the same time, and Sophia will be the one to tell you guys about it.
In projective geometry, you can do something called compactification of the Euclidean plane by adding points at infinity. Each family of parallel lines meets at a unique point at infinity, and the collection of such points forms the line at infinity. Of course, this line looks more like a circle in our drawing here, because we can't really represent on screen a line at infinity. But I hope you get the idea. Anyway, the correct and precise Minkowski metric that you get, written in spherical coordinates after moving infinitely away from the massive body, is this. 2. Metric right on the surface. What happens if we take the interior Schwarzschild metric and study it for a point on the surface on the spherical body? Well, let's see. Check this out. We just recovered the exterior Schwarzschild metric at a point r equals r, so on its surface. I mean, it makes sense if you think about it. 3. Singularity. Now we're ready for the coolest part of the video. Let's start with the exterior metric, since it's the simplest one. And to make things more tangible, let us pick the planet Earth as our massive body. Recall the value of the gravitational constant g and the speed of light c. First, we substitute these values. Then we can clearly see that if r equals 2 gm divided by c squared, which is approximately 8.87 millimeters, we get the following metric. which is actually nonsense because we just contradicted ourselves. Did you catch where exactly that was? Well, you don't need to know the exact radius of the Earth off the top of your head, which is 6,371 kilometers, by the way, in order to notice that a point at the distance 8.87 millimeters from the center is located inside our planet. And therefore, we cannot use the exterior Schwarzschild metric as we just did. This is a contradiction. The correct approach would be to use the interior Schwarzschild metric. Let's change reality a little bit and assume the same identical situation, with the only tiny difference being that the radius of Earth is less than 8.87 millimeters. In order to make that true, we'd have to compress the entire mass of our planet to a volume equivalent to a ball with radius less than 8.87 millimeters. This would be an extremely dense object, but if it were created, then all of a sudden this metric turns out to be a consistent physical model, except for the infinite radial component that we will discuss in a moment. But in a certain sense, it is consistent, since we're located outside the body now. In this metric, as you can see, the time component is 0, which means that time appears frozen to distant observers. The radial component diverges, indicating a coordinate singularity, not a physical one. The appropriate change of coordinates would allow us to see that, but we will not discuss it here. Congratulations, you just learned a scientific formula for producing a black hole. Because even though a body having its radius less than the Schwarzschild radius doesn't automatically make it a black hole, so the radius is not necessarily 0, gravity becomes strong enough that the object would eventually collapse into itself, ultimately forming a singularity. So we can transform any massive object, including the Earth, into a black hole. All we have to do is find a way of compressing it until it crosses the physical limit, below which its radius is less than twice the gravitational constant times the mass of the body, divided by the speed of light squared. This physical limit is called the event horizon, and the limiting radius is the Schwarzschild radius. A question that can naturally pop up in your head right now is this. So if I can turn any object with mass into a black hole, then what really counts here is the ratio of mass over volume. As long as the volume is tiny, I don't need a lot of mass to produce a singularity. But then what happens when I want to transform a very little mass into a black hole by compressing it inside of a volume equivalent to a ball of radius less than the Planck scale? If the object's radius becomes smaller than its Schwarzschild radius, it forms a black hole, regardless of how large or small the mass is. For small masses, the Schwarzschild radius becomes extremely tiny. If the Schwarzschild radius drops below the Planck length, then the black hole description enters a regime where general relativity and quantum mechanics blend together, and quantum gravity effects dominate. Currently, nobody knows what happens in this quantum gravity realm. The only thing we can say for sure is that classical general relativity is not valid anymore, and that quantum mechanics and gravity must both somehow be taken into account. Such weird objects are called Planck scale black holes, or micro black holes, and that's where speculations about them come from. If you want to see an example in which we calculate what it would take to turn an electron into a black hole, check out the PDF link in the description. The disclaimer is that we would clearly fail at this attempt, since we still have no theory of quantum gravity that matches experiments. But anyway, it's still useful to play with these ideas in order to grasp the intuition behind the math. The last thing I'll say about it is that for our planet Earth, or any other ordinary massive object that is not a black hole, the Schwarzschild radius is much smaller than its physical radius. So the event horizon is located inside the body and has no physical effect for all non-black hole objects, so objects with Schwarzschild radius less than their actual radius. Only when the object is compressed so that its radius becomes smaller than or equal to its Schwarzschild radius does the horizon find itself outside the matter distribution and the object becomes a black hole. In this video, we covered two of the most important solutions of Einstein's field equations, the Minkowski and the Schwarzschild metrics. If you'd like to see a list of famous solutions, check out the PDF link in the description. And if you want a deeper description of each, we attached an amazing material called Catalog of Spacetime in the description of this video.
Einstein's equations may look compact, but they become a complex system of relations between tensors that describes spacetime and how it bends in reaction to matter and energy. Each solution built from symmetric tensors shows a possible geometry of spacetime. They could be flat, curved, or a mix of both. I hope you guys liked this compilation. Of course, we couldn't go in too much detail here, but I think it's a very, very good introduction for you guys who want to learn more about general relativity from the mathematical point of view or the physical point of view. If you have any suggestions, let us know in the comments section below or just email us. You can easily find our contact in our website. So look for it there.